Imagine a star without atoms. A star with no fusion, no fire, no light. A star that doesn't shine but still pulls on space and time as if it were one of the cosmos's greatest titans. Now imagine that this star is not made of anything we've ever touched or seen, not gas, not plasma, not dust, but pure force. Just quantum fields and gravity, locked in an eerie, perfect balance. A gravitational phantom whispering through the dark fabric of space-time. But before we continue, subscribe to the channel so you don't miss out on any of these videos. We call it the Boson star, a ghostly giant made not of ordinary matter, but of particles that barely play by the same rules as the matter around you. These are not protons or electrons. They're bosons, particles of pure interaction. When normal matter jostles and collides, bosons can move in perfect harmony, stacking into states so strange that we had to build quantum mechanics just to explain them. Now, imagine billions upon billions of those bosons forming an invisible, massive object that could lurk at the center of a galaxy, and you might never know it was there. And here's the twist: some scientists believe that these phantom stars might be real. Not just theoretical whispers from the equations of quantum gravity, but actual objects drifting through the universe. We may have even seen one already, and mistaken it for a black hole. In a universe filled with familiar things, glowing stars, whirling galaxies, collapsing supernovae, boson stars feel like an echo from an alternate reality. They are what happens when gravity dances with quantum mechanics without the rules we're used to. No fusion engines. No atomic structures. No surface. Just a gravitational field formed by waves of probability. This isn't science fiction. This is physics, right at the edge of what we understand. So what are these strange objects? Where do they come from? What do they mean for our understanding of mass, gravity, and dark matter? Could they even solve some of the most pressing mysteries in cosmology? Over the next few hours, we will dive into the ghostly heart of boson stars. We'll uncover how they defy normal physics, how they could hide in plain sight, and why they could be among the most important cosmic objects in the universe, if they exist. This is not just a story about stars. It's a story about the strange architecture of the universe itself. A story of silent giants. Of invisible matter. Of pure force coalescing into form. This is the tale of the boson star, a ghost in the cosmos that may hold secrets more massive than any black hole. In the vast library of theoretical physics, there are concepts so exotic they seem more like metaphysical poetry than hard science. Yet they emerge naturally from our most advanced equations. One such concept is the boson star. It's not just an unusual type of star, it's an entirely different category of object, one that rewrites the basic script of stellar formation and structure. To understand just how strange boson stars are, you have to look at what they're made of, not the familiar particles of matter we know, but an entirely different breed of particle. Everything in the visible universe, stars, planets, you, me, is built from fermions, particles like protons, neutrons, and electrons. These particles obey the Pauli exclusion principle, which essentially means that no two fermions can occupy the same quantum state. That principle is what gives matter its structure, what keeps atoms from collapsing in on themselves, and what allows complex matter to exist at all. But boson stars? They don't play by those rules. Because boson stars are made of bosons, particles that obey entirely different laws. Bosons don't mind sharing. In fact, they prefer it. Where fermions repel, bosons align. They can all occupy the same state, move together, resonate together, even act as one. That's why photons, which are bosons, can exist in coherent beams like lasers. And that's why a large collection of bosons can, under the right conditions, form something deeply strange, a structureless, smooth, gravitational object that doesn't need internal pressure to resist collapse the way ordinary stars do. Boson stars are, as far as we know, entirely theoretical. No one has directly observed one. But they emerge naturally from the marriage of quantum field theory and general relativity. If bosons exist in large enough quantities, and if they're the right kind of boson, they can clump together under gravity, not as atoms or molecules, but as a vast, coherent wave of quantum energy. Imagine a cloud of particles, all in the same state, gravitationally bound, radiating no light, and leaving no solid surface to speak of. That's the boson star. Unlike traditional stars, there is no nuclear fusion inside. There are no atoms undergoing pressure-cooked reactions. There's no crust, no layered core, no convection zones, no light pressure balancing against gravity. Instead, there's just gravity pulling inward, and the quantum nature of bosons pushing back. This balancing act, between gravitational attraction and quantum dispersion, is delicate. But if the conditions are just right, the result is stable, a star-like object that, despite being made of something fundamentally different, holds together. The boson star is a creature of harmony. It doesn't roar with the fire of fusion, or the explosive death of a supernova. It hums silently, in the language of wave functions and curved spacetime. It is as if nature built a star out of probability itself. What makes this so compelling is that boson stars don't require exotic new physics to exist. The concept is grounded in equations we've had for decades: Einstein's field equations from general relativity and the Schrödinger or Klein-Gordon equations from quantum mechanics. When you put them together and solve them for a massive bosonic field, what you get is not just a possibility, but a prediction, a compact, massive object that looks like a star, but glows with nothing at all. And therein lies the mystery. Because if such objects are out there, they would be all but invisible. No electromagnetic signature. No light. No neutrinos. Just mass, possibly enormous mass, warping space around it, shaping the motion of stars, bending light from galaxies behind them, perhaps even mimicking the silhouette of a black hole. And unlike black holes, which require the catastrophic collapse of a massive star, boson stars could form in quieter, more subtle ways. They could have been born not from death, but from the early whispers of the universe itself. Their existence might even precede atoms, formed from primordial bosonic fields moments after the Big Bang. But they would still have structure. They would still have gravity. And they would still move through the universe like silent giants, invisible yet powerful, ancient yet ageless. In this light, boson stars are not just theoretical curiosities. They're possible keys to understanding phenomena we currently struggle to explain, like dark matter, like gravitational anomalies, like the shadows we see in the hearts of distant galaxies that we've simply assumed must be black holes. Because if even one boson star exists, it means the universe has found a second path to forming stellar mass objects. Not through atoms, heat, and fire, but through unity. Through coherence. Through force fields and probability waves shaped into form by the curvature of spacetime. If you looked at a boson star from the outside, it would look like nothing. No light. No flickering surface. No emissions in the visible, infrared, or even radio bands. In fact, it might look like empty space, except for the way it bends light around it, or tugs on nearby objects with its gravity. That's because boson stars are not stars in any traditional sense. They don't shine, they don't burn, and they don't die the way normal stars do. They exist as gravitationally bound condensations of pure quantum fields, held together not by heat or radiation pressure, but by gravity alone, delicately counterbalanced by the quantum properties of bosons themselves. Ordinary stars are basically gigantic nuclear engines. The Sun, for instance, burns through about 600 million tons of hydrogen every second, fusing atoms into helium in a process that releases titanic amounts of energy. That fusion generates pressure, which pushes outward against the force of gravity trying to collapse the star inward. This balance, between fusion-driven outward pressure and gravitational inward pull, is what defines the life of a normal star. Boson stars have no such balancing act. There is no internal furnace. No burning fuel. No atoms at all. Just a massive cloud of bosons, overlapping in perfect synchrony, forming a self-consistent gravitational structure. These bosons are not bouncing around like particles in a gas. Instead, they exist in a state of extreme quantum coherence, acting more like a standing wave or a field configuration than a bunch of individual particles. And because boson stars don't contain atoms, they also don't have electrons, which means they don't emit or interact with electromagnetic radiation in the usual ways. There's no mechanism for producing light. No photons bouncing off surfaces. No atomic transitions radiating energy. A boson star could have the mass of a neutron star or more, and yet not emit a single visible photon. It would be as if the entire object was cloaked from detection, unless you were watching how it distorts space. Their gravity, however, is very real. Boson stars bend the space around them just like any massive object would. If you pass near one, you'd feel its presence as a subtle shift in trajectory, a gravitational deflection. If light passed behind it, you might see gravitational lensing, the warping of background starlight. But there would be no glow. No radiation to betray its structure. Just gravity holding itself together. This makes boson stars radically different not only from normal stars, but from almost every object we typically associate with mass. Even neutron stars, those compact remnants of supernovae, are still made of fermionic matter, neutrons packed into a solid, crusty core. They emit beams of radiation, especially if they're pulsars. But boson stars? They're smooth. They have no crust. No surface. No atomic makeup. They are continuous and diffuse on a quantum level, with their mass density smoothly falling off from the center like a mist that gets thinner and thinner until it fades into the vacuum of space. The defining feature of a boson star is that it's held together not by anything you can touch or see, but by the geometry of space-time and the properties of wave functions. It's like a self-sustaining knot in the fabric of the universe, a balance between the spreading tendency of quantum fields and the pinching effect of gravity. This balance allows a boson star to persist, potentially for billions of years, without burning out or collapsing, and without ever emitting light. Now imagine how different the cosmos would appear if a significant portion of its mass were tied up in objects like this. We might be surrounded by dark stars, their presence felt only through the movements of nearby galaxies or the bending of distant starlight. And what's more, their formation might not be a rare, special case event. It could be a fundamental mode of structure in the universe, overlooked simply because we never thought to look for something so quiet. Because when it comes to boson stars, silence is not emptiness. Silence is structure. It's gravity humming at quantum frequencies. It's the universe forming something immense, but invisible. Something that refuses to shine, yet warps everything around it. And that's why boson stars are not just unusual, they're unprecedented. They're stars in name only. They don't light the night sky. They don't warm orbiting worlds. They don't leave colorful remnants when they die. They just are. Coherent, cold, and almost perfectly hidden. To truly grasp the haunting elegance of boson stars, we need to understand the building blocks they're made from, bosons. These aren't just another class of particle. They are fundamentally different from the matter that makes up your body, the earth beneath your feet, and the stars overhead. In physics, particles fall into two major categories, fermions and bosons. And the distinction between the two is not just academic, it defines the very architecture of the universe. Let's start with fermions. These are the particles that make up what we traditionally think of as matter. Electrons, protons, and neutrons are all fermions. What makes them special is a rule called the Pauli exclusion principle. This principle forbids two identical fermions from occupying the same quantum state at the same time. That sounds abstract, but it has enormous consequences. It's the reason atoms have structure. It's why electrons orbit the nucleus in layers. It's why matter is solid and why you can't walk through walls. Fermions are the rule makers. They build the skeleton of reality. They define space, boundaries, and individuality in the quantum world. Bosons, on the other hand, are the great cooperators of the particle world. They don't obey the Pauli exclusion principle. In fact, they do the opposite. Bosons love to be in the same state. If one boson is in a certain place, with a certain spin and energy, another boson will happily join it. This tendency to pile up in the same state is what gives rise to some of the most spectacular quantum effects in nature, like lasers and superconductivity. So what kinds of particles are bosons? Some of the most important ones are the force carriers in the standard model of particle physics. Photons, the particles of light, are bosons. So are gluons, which hold quarks together inside protons and neutrons. W and Z bosons carry the weak nuclear force. And the graviton, if it exists, would also be a boson, mediating gravity across space. Even the Higgs boson, the particle that gives others their mass, is, as the name suggests, a boson. But not all bosons are force carriers. Some could be mass-bearing scalar or vector fields, hypothetical particles that fill the universe in quiet, hidden ways. These are the kinds of bosons that boson stars are thought to be made from. One particularly popular candidate is the axion, a light, neutral boson proposed to explain certain unsolved problems in particle physics and cosmology. Axions and similar particles could be stable, nearly invisible, and so numerous that they might form the dark matter halo around galaxies. And under the right conditions, these bosons could clump together, not into atoms, but into vast clouds, held in shape by gravity. That's when you get a boson star. Now here's where things get really interesting. Because bosons can all occupy the same quantum state, they behave not like billiard balls but like waves. They don't bump into each other. They merge, interfere, and resonate. So instead of thinking of a boson star as a collection of individual particles, it's better to think of it as a single, giant quantum wave, oscillating in the geometry of curved spacetime. This wave-like behavior is what allows boson stars to exist without pressure or fusion. The wave spreads out due to quantum uncertainty, but gravity pulls it inward. These two effects can balance, creating a stable, self-sustaining configuration. The bosons are not confined in the way atoms are in a solid. They're delocalized, blurred, like mist woven into the fabric of space. From a physics standpoint, this is both revolutionary and elegant. Fermionic matter resists compression due to the Pauli principle. That's what supports white dwarfs and neutron stars against gravitational collapse. But bosonic matter has no such resistance. It can collapse more freely, yet through its quantum wave nature, it can still avoid forming a singularity. It can find a new kind of balance. That's why boson stars can be incredibly compact and massive, yet avoid becoming black holes. They ride a knife's edge between collapse and dispersion, bound together by the strange union of general relativity and quantum field theory. And this matters, hugely, for our understanding of the cosmos. Because if bosons like axions or ultralight scalars do exist, then the ingredients for boson stars are already written into the universe's rulebook. We wouldn't need new laws, just new observations. It's not a stretch of imagination. It's an invitation to look deeper. Bosons, in this sense, are the symphony players of the quantum world. Where fermions form structure through resistance, bosons build harmony through coherence. And boson stars are their most majestic performance, a vast, unseen melody composed not of fire and flame, but of fields and frequencies. In the ordinary world, particles behave like individuals. Each car has its own lane. Each person has their own space. Even in the microscopic world of atoms, fermions, like electrons and protons, follow this same rule. They repel, they exclude, they cannot occupy the same state. But bosons? They don't just break this rule. They rewrite the social code of quantum mechanics. Bosons can occupy the same quantum state as one another. In fact, the more bosons you have in one state, the more likely it becomes that others will join them. It's like a gravitational well in quantum probability. Once a state starts to be filled with bosons, it becomes a magnet for more. This is called Bose-Einstein statistics, and it gives rise to one of the most extraordinary phenomena in physics, the Bose-Einstein condensate, or BC. A Bose-Einstein condensate isn't just a bunch of particles sticking close together. It's something much weirder, a state of matter where all the bosons collapse into the same ground state, becoming indistinguishable, acting as one unified quantum entity. It's as if every particle gives up its individuality and merges into a single, collective existence. Imagine a cloud of millions of particles that moves like a single wave, responding to forces as a single whole, rather than as a swarm of parts. BECs were theorized in the early 20th century by Satyendra Nath Bose and Albert Einstein, who realized that at very low temperatures, bosons should begin behaving not like particles, but like overlapping waves. But it wasn't until 1995 that scientists were able to cool rubidium atoms down to a few billionths of a degree above absolute zero and observe a real BC in the lab. What they found was revolutionary, a strange, ghostly blob where quantum effects dominated on a macroscopic scale. These condensates have bizarre properties. They can flow without friction, like superfluids. They can climb walls. They can interfere with themselves like a single giant matter wave. In some cases, they can even exhibit quantum vortices, regions where the entire fluid circulates with a quantized amount of angular momentum. Now imagine this same kind of quantum collectivity, not in a lab, but on a cosmic scale. That's what a boson star might be, a gravitational Bose-Einstein condensate, made not of rubidium atoms chilled in magnetic traps, but of fundamental bosons, like axions or ultralight scalars, held together by gravity alone. In such a star, billions upon billions of bosons would condense into the same quantum state, overlapping and reinforcing each other, behaving as one enormous wave. There's no surface, no shell, no lattice. Just a single, coherent quantum structure that extends across light years. This collective behavior is the very foundation of how boson stars could even exist. Because bosons don't resist crowding together, they can collapse under gravity in a way that fermions cannot. But they don't collapse endlessly into a singularity either, because quantum pressure, arising from the uncertainty principle, still spreads them out. The result is a unique equilibrium, governed not by heat or fusion or electromagnetic repulsion, but by the gentle dance between gravity and quantum mechanics. This collective nature also means that boson stars don't fragment. They're not made of chunks or shells. They are smooth and unified, entirely unlike any normal star. Their density can be highest at the center, gradually falling off in a smooth gradient, but there is no sharp boundary. The whole star behaves like a standing wave pattern of mass and energy. And because it's a single quantum state, its behavior is dictated by wave equations, not by thermodynamic ones. It's almost more accurate to call it a quantum field object than a star in the traditional sense. The most mind-bending part? This quantum coherence means that the boson star could react to disturbances in profoundly non-classical ways. Instead of simply wobbling or shaking like a solid object, it could develop wave instabilities, resonances, or even collapse into different quantum modes. In theory, some boson stars might be metastable, fluctuating between different configurations based on external gravitational interactions or quantum tunneling events. In the heart of every boson star, then, is this astounding truth: it is not made of many things, but of one thing, repeating itself, echoing through spacetime in perfect quantum harmony. Where ordinary stars are collections of colliding, resisting particles, boson stars are the ultimate collective, a star where individuality has been erased, where the laws of crowd behavior are flipped, and where the wave function isn't just a mathematical abstraction, but the very shape of the star itself. The idea of the boson star didn't come from science fiction. It wasn't dreamed up in a novel, or imagined as a cinematic plot twist. It emerged quietly from the cold machinery of physics, the mathematical fusion of two of our most successful, yet philosophically incompatible, theories, general relativity and quantum field theory. And like many breakthroughs in science, it began not with certainty, but with a question. In the 1960s, physicists were deep in the throes of reconciling the physics of the very large with the physics of the very small. On one side stood Einstein's general relativity, a majestic theory that describes how mass and energy warp the fabric of spacetime. On the other side loomed quantum field theory, which explains how particles emerge as excitations of underlying fields, obeying the weird and often unintuitive laws of quantum mechanics. For decades, these two pillars of modern physics had stood strong, separately. But putting them together? That's where things got complicated. Gravity doesn't play nicely at the quantum level, and quantum mechanics resists being expressed in the geometrical language of relativity. But despite this tension, theoretical physicists began to explore what might happen if certain quantum fields, especially scalar fields, were allowed to interact with gravity in curved spacetime. Enter the concept of the boson star. In 1968, physicists Kopp and independently Ruffini and Bonazzola proposed a radical idea. They took the equations that describe massive scalar fields, like the Klein-Gordon equation, which is a relativistic cousin of the Schrödinger equation, and coupled them to Einstein's field equations of gravity. What they discovered was astonishing. Under the right conditions, a massive, self-gravitating configuration of bosonic field could form a stable, localized structure. It didn't blow apart from internal pressure. It didn't collapse into a singularity. It just existed. And crucially, it didn't require any exotic forces. No new dimensions. No black hole singularities or event horizons. Just ordinary gravity and a hypothetical bosonic field. The balance between gravitational attraction and the dispersive effects of the scalar field could create a stable, compact object, a boson star. These early models assumed non-interacting bosons, essentially, scalar fields with only mass and no self-coupling. Even in these simplest cases, the results were compelling. The boson star appeared as a dense, smooth distribution of energy and mass, centered in space, falling off gradually as you moved away from the core. No crust. No sharp edges. Just a continuous blob of curved spacetime shaped by a standing wave of quantum field energy. As the theory matured through the 1970s and 80s, more complex versions of the boson star were developed. Physicists began to consider self-interacting bosons, introducing terms into the equations to simulate repulsion or attraction within the field. These interactions drastically changed the properties of the star, making it more compact, altering its maximum mass, or even introducing oscillatory behavior. Later still came rotating boson stars, multi-state configurations, charged versions, and even so-called Q stars, which extended the boson star concept into more exotic field theories. With each variation, theorists explored what would happen if different types of bosons, massive, massless, charged, spinning, were subjected to the gravitational cauldron of Einstein's universe. What was clear, even in the earliest stages, was that boson stars offered a whole new class of astrophysical object. They weren't just theoretical oddities. They were solutions, mathematical artifacts with the potential to be real, physical structures in the universe. And they appeared without the need for extraordinary assumptions. Given the right bosonic particles, the right field parameters, and enough mass, the universe should be able to make them. In a way, the birth of the boson star was less a dramatic discovery and more a quiet inevitability. Once you take seriously the possibility that the universe is filled with fields, and quantum mechanics tells us it is, and that gravity shapes and responds to energy in all forms, it becomes almost unavoidable that new forms of structure will emerge. Boson stars were born not in the glow of a telescope lens or in the heat of particle collisions, but in the stark, beautiful logic of mathematics. They were the children of curvature and coherence, predicted not because anyone was looking for them, but because the equations pointed the way. And yet, as with many great ideas in physics, their real significance would take time to unfold. Because the 1960s were still early days. No one had yet observed a gravitational wave. Dark matter was still an unsolved puzzle whispered about in the margins of astrophysical journals. And the idea that black holes might have doppelgangers made of pure quantum fields? That was an idea far ahead of its time. Still, the seed had been planted. Boson stars were now part of the lexicon of theoretical physics. Waiting. Growing in complexity. Taking shape in the minds of those who dared to imagine stars without fire, ghostly giants made not of matter, but of fields. The genius of boson stars lies not just in their elegance but in the unlikely marriage of two towering figures in physics, Einstein and Schrödinger. One gave us the curvature of spacetime. The other gave us the fluid, ghost-like wave of quantum mechanics. And yet, the idea of boson stars emerges exactly where their ideas meet, in the friction zone between the deterministic geometry of the universe and the probabilistic haze of the quantum world. Let's break this strange fusion down. Albert Einstein's theory of general relativity describes gravity not as a force in the traditional Newtonian sense, but as the warping of space-time by mass and energy. His famous field equations tell us that energy, whether it be from matter, radiation, or even pressure, tells space-time how to curve. And in turn, that curvature tells objects how to move. The equations are beautiful, profound, and geometric. But they are also classical. They assume that energy and mass behave predictably, continuously, like a smooth fluid. On the other hand, Erwin Schrödinger's equation describes the behavior of particles at the quantum scale. Unlike the certainties of classical physics, Schrödinger's equation is probabilistic. It describes how a quantum state evolves over time, not as a point-like particle, but as a wave function that represents all possible positions and momenta. This wave function spreads, interferes, and evolves according to a complex set of rules rooted in uncertainty and superposition. Now here's the magic. Even though Einstein and Schrödinger were working in different realms, one in the cosmic ballet of stars and galaxies, the other in the jittery world of atoms and electrons, their equations can be combined. And when you do, you get something utterly new, objects whose structure is governed by both space-time curvature and quantum wave coherence. Boson stars arise from such a union. The process starts with a quantum field, most commonly a scalar field, which can be thought of as a smooth, continuous energy field that permeates space. Think of the Klein-Gordon equation, a relativistic extension of Schrödinger's equation that describes how such fields evolve in time and space. Then, couple that equation with Einstein's field equations, which describe how the energy from that scalar field curves spacetime. Mathematically, this means inserting the energy-momentum tensor of the scalar field into the Einstein equations and simultaneously solving both sets of equations. What you get is a self-consistent solution, a scalar field configuration that warps spacetime and is itself affected by that very curvature. The result is not a singularity, not an explosion, but a stable structure, a boson star. What's truly striking is that these objects don't require a surface. The quantum field that makes up the boson star can extend infinitely, just growing weaker as you move away from the center. There is no hard shell, no crust of fermionic matter. The structure is defined entirely by the amplitude and frequency of the field, and by the gravitational well it creates. The peak of the wave function sits in the core, where the mass density is highest, and gently falls away in every direction like a ripple through curved space. In this configuration, you're not dealing with particles bouncing around in a container, like in a gas. You're dealing with a giant, standing quantum wave, shaped by and shaping the gravitational landscape around it. The entire star is described by a single wave function or a superposition of wave functions, solutions to the Klein-Gordon equation in curved spacetime. This coupling brings out unique properties. For example, the gravitational field serves as a kind of quantum trap that holds the bosons together. But unlike in neutron stars, where degeneracy pressure supports the object, in boson stars it's the quantum uncertainty and the wave-like dispersion of the field that balances gravity. The bosons, all in the same quantum state, form a kind of gravitational Bose-Einstein condensate, coherent, cold, and massive. And all of this is possible without needing any exotic modifications to the laws of physics. This isn't string theory or a speculative new dimension. It's just the standard model extended by one hypothetical boson field, plus general relativity. In fact, the only speculative ingredient is the boson itself, though many such candidates already exist in the wild world of particle physics, axions, dilatants, and other scalar or vector bosons predicted by theories beyond the standard model. So what we have is a kind of quantum gravitational equilibrium. A star not born of thermonuclear ignition, but of mathematical resonance. The equations don't just describe the star, they are the star. The wave function is the structure. The gravity is the boundary. Together, Einstein and Schrödinger give us an entirely new way for the universe to hold mass, to warp space, and perhaps, if such stars exist, to hide from light while revealing themselves in the subtle bending of spacetime. It's a poetic convergence of physics, where Einstein's curvature provides the architecture, and Schrödinger's uncertainty breathes life into the form. A boson star is a dialogue between gravity and wave function, written not in atoms, but in fields. And in that quiet conversation, a new kind of star is born, not from fire, but from pure form. In the everyday world, mass feels like something tangible. You pick up a rock, you feel its weight. You accelerate your car, and the engine strains against inertia. In our minds, mass is inseparable from substance, atoms, molecules, particles, solid stuff. But the deeper we dive into the quantum realm, and especially into the physics of boson stars, that notion begins to dissolve. Because in the quantum universe, mass doesn't always come from matter. Sometimes it comes from the shape of a wave. In boson stars, there may be no traditional matter at all. No particles with well-defined positions. No atoms with mass in the classical sense. Yet, these ghostly stars can warp spacetime as if they contained the mass of an entire sun. They can bend light, attract other bodies gravitationally, and, if dense enough, imitate the appearance of a black hole. All without a single proton. All without a single atom. So where does the mass come from? The answer lies in a profound and subtle feature of quantum field theory. Energy itself is mass. And more specifically, a field configuration, even if it contains no localized particles, can carry energy. When that energy is confined, when it's bound together by its own gravity, it can act like mass. It can curve spacetime. And to an outside observer, it's indistinguishable from an object made of solid, baryonic matter. Let's step back. According to Einstein's famous equation, E equals mc squared, mass and energy are interchangeable. That's not just a theoretical curiosity. It's the basis for nuclear power, radioactive decay, and even the inner workings of stars. But this also means that anything with energy must also, in a sense, have mass. And a quantum field, like the scalar field that might make up a boson star, can carry energy in its oscillations, in its gradients, and in its potential. Picture a boson star as a giant oscillating wave, a standing pattern of field intensity localized in a region of space. The bosonic field is fluctuating in a specific configuration, vibrating, curving, resonating. These vibrations, even though they aren't particles, in the traditional sense, carry energy. And that energy density is enough to give rise to gravitational curvature. In general relativity, any energy density, whether from radiation, matter, or a quantum field, can warp spacetime. So the mass of a boson star is not in particles with rest mass, it's in the collective wave of the field. There is no need for mass to come from a particle at all. The very shape of the wave function, the way the field is arranged in space and time, carries an effective mass that spacetime responds to. It's like a drumhead vibrating in silence, and yet the air still ripples around it. To make it even more fascinating, the scalar field in many models of boson stars has no interaction with the electromagnetic field. It doesn't couple with light. It doesn't radiate. It's transparent. And yet, it can be enormously massive, simply because its field configuration is dense with energy. In physics, we call this a non-topological soliton, a self-contained, stable wave configuration that maintains its form due to internal balancing forces. In some sense, the boson star is mass without matter. No rest mass. No atomic structure. Just energy bound in a coherent quantum form. This is not unprecedented in physics. Photons, for instance, have no rest mass, but a high-energy beam of light can, in theory, produce gravitational effects. But boson stars are even more concentrated, more gravitationally bound, and potentially much more massive. There's another twist. In many field theories, the bosonic field that makes up a boson star isn't static. It oscillates in time. But because these oscillations are uniform across the entire object and don't emit radiation, they don't decay away like vibrations in normal matter. Instead, they maintain a stationary energy density, meaning the mass of the boson star can remain stable for astronomical timescales. And here's where the philosophy of physics collides with its mathematics. Boson stars ask us to rethink what it means to be something in the universe. If you strip away the particles, the atoms, the electromagnetic emissions, what's left? If the only thing that remains is a standing wave in curved space that holds itself together and influences the cosmos, is that not still something? Perhaps even something profound? Mass, in the context of boson stars, becomes a geometric phenomenon. It's not a pile of stuff. It's a pattern. A pattern of energy so perfect, so balanced, that it drags spacetime into its rhythm. It bends light, draws matter toward it, and yet reveals nothing of itself, not through radiation, not through texture, not through heat. Only through the gravitational whisper that says, "I am here." And in that whisper, mass speaks, without matter. In laboratories on Earth, Bose-Einstein condensates, BECs, are among the coldest things humans have ever created. They are also among the strangest. By cooling a dilute gas of bosonic atoms to temperatures within a fraction of a billionth of a degree above absolute zero, scientists can coax them into a collective quantum state. Suddenly, what was once a random swarm of individual particles becomes something astonishing, a single, unified quantum entity. All the atoms collapse into the lowest possible energy state and act as one coherent wave. Now, imagine scaling that phenomenon up from a tiny glass chamber the size of your palm to something the size of a neutron star or larger. Something with the mass of a sun. Something that doesn't need extreme cooling, because it formed not in a laboratory, but in space itself, through the grand forces of gravity and quantum fields. That's what a boson star could be, a cosmic Bose-Einstein condensate, a quantum collective not of atoms, but of elementary bosons, perhaps axions, or some other ultralight scalar particle. The comparison is not just poetic, it's scientifically grounded. Both laboratory BECs and theoretical boson stars are governed by the same principles of quantum mechanics. Both involve bosons sharing the same quantum state, behaving as a single macroscopic wave function. In a lab, this requires cooling particles down until their thermal motion is nearly non-existent, because any jostling would break the delicate coherence needed for condensation. But in a boson star, gravity takes the place of cooling. The bosons are drawn together, but they don't collide in the violent way fermions do. Instead, they merge, aligning their phases and forming a stable configuration in curved spacetime. In fact, the mathematics used to describe BECs in the lab is eerily similar to the equations used to model boson stars. The Gross-Pitaevsky equation, which governs the dynamics of atomic BECs, is closely related to the Klein-Gordon equation coupled to general relativity, the very framework used in boson star theory. Both describe the evolution of a scalar field's amplitude and phase. Both produce soliton-like solutions under the right conditions. And both result in a macroscopic wave function, a single complex function that describes the entire object. This quantum coherence gives boson stars their most extraordinary quality. Their structure is not built from particle interactions or layers of material, but from interference patterns of probability waves. Just as a BC can form a vortex that spins without friction, a rotating boson star could exhibit strange behaviors not seen in classical astrophysical objects. It might develop internal phase patterns. It might shift shape slightly depending on gravitational perturbations. It might even exhibit quantum tunneling at cosmic scales, transitioning between different states under certain extreme conditions. In the lab, BECs have revealed some of the most surreal phenomena in physics: atoms behaving as waves, clouds of matter interfering like light, superfluidity, quantized vortices. These properties don't just scale down to zero, they can scale up. If boson stars are indeed cosmic condensates, then these quantum behaviors might extend over kilometers, or even hundreds of kilometers, shaping the very identity of the star. Consider what this means. In a neutron star, degeneracy pressure from neutrons resists collapse. The particles are jammed together, bouncing off one another with incredible force. But in a boson star, there's no such repulsion. The bosons slide past one another, overlapping perfectly, as if they were ripples on the same pond. Yet this doesn't lead to collapse, because the quantum wave function of the condensate inherently spreads out, resisting tight localization due to the Heisenberg uncertainty principle. Gravity pulls in, the quantum field spreads out, and somewhere in between lies balance. There is a strange beauty here, a harmony where classical and quantum forces meet. In laboratory BECS, we glimpse it on tiny scales, for brief moments before decoherence destroys the state. But in boson stars, that harmony could persist for billions of years, embedded into the fabric of galaxies, quietly orbiting through dark matter halos, revealing themselves only through gravity's soft pull. It's also worth noting that while BECS on Earth are composed of composite bosons, atoms made of multiple fermions arranged in a bosonic configuration, boson stars are thought to be composed of fundamental bosons, like axions or ultralight scalar particles. These are not made of anything smaller. They are quantum fields in their own right, and in large numbers, they can form something even more perfect than lab-based BECS, a field condensate that is smooth, featureless, and massive. This kind of condensate doesn't just flow. It bends the structure of spacetime. It curves light paths. It might even trap electromagnetic waves or mimic the gravitational signature of a black hole, without ever emitting a single photon. The coherence of a boson star could therefore have a cosmological signature, one we might eventually detect through gravitational lensing, wave echoes from binary mergers, or subtle distortions in the motions of stars. And unlike BECS, which are fragile and require artificial containment, boson stars are self-contained. Their gravity does the job of the magnetic traps used in labs. Their quantum nature ensures coherence, and the absence of internal thermal motion or scattering means they can survive in the harsh vacuum of space, indefinitely. Where laboratory BECS last for seconds, boson stars could last for the age of the universe. There is even a growing community of physicists who speculate that dark matter halos surrounding galaxies could be made of diffuse, gravitationally bound condensates of ultralight bosons. These wouldn't be dense boson stars in the traditional sense, but bosonic field configurations spread across kiloparsecs, shaped by the same quantum principles. In this view, boson stars would be the high-density counterparts, condensed knots in a wider quantum fog that permeates the universe. The implications are staggering. If boson stars are real, they represent a new state of matter, a kind of gravitational quantum crystal, invisible to light, yet massive enough to steer galaxies. And unlike anything else in the universe, they are coherent from the inside out. Not heat-driven, not matter-bound, but wave-bound. In the 20th century, we learned how to cool gases until their atoms marched in perfect quantum lockstep. In the 21st, we may discover that nature had already done something far more spectacular, creating entire stars from that same principle, floating in the cosmos, unnoticed, waiting to be revealed. In the physical universe, balance is rarely still. It's a constant negotiation, a tension between forces pulling in opposite directions. In a conventional star like our Sun, balance means gravity pulling inward, trying to collapse the mass, while radiation pressure from nuclear fusion pushes outward. The star lives in a dynamic equilibrium, teetering between implosion and explosion. But what happens when you remove the fusion? When there's no light, no atoms, no heat? What if all you're left with is gravity, and something so faint and fragile it can't even be touched, a quantum field? Boson stars live in that strange, silent zone. They are stabilized not by outward blasts of energy, or the pressure of burning gases, but by a far subtler force, quantum pressure, the pushback of uncertainty and coherence. The interplay between gravitational attraction and quantum wave behavior creates a structure unlike anything else we know, a perfectly poised object where the fabric of reality itself is the architect. To understand this balance, let's revisit the key ingredients. First, gravity. In any self-gravitating system, mass creates a pull. The more compact the system becomes, the stronger this inward pull grows. If unchecked, this leads to catastrophic collapse, as seen in black holes. The star gets smaller, denser, and eventually reaches a point where not even light can escape. But boson stars, though massive, avoid this fate. Why? Because of quantum pressure. This isn't pressure like steam building in a kettle. It's not thermal motion or particle collisions. It's born out of the Heisenberg uncertainty principle, which states that the more you try to confine a particle in space, the more uncertain its momentum becomes. In essence, if you try to squeeze a wave function too tightly, it pushes back. The field spreads, not because it wants to, but because it has to. For boson stars, this means that as gravity tries to pull the scalar field inward, the quantum wave function begins to spread outward in response. It's not repulsion, it's uncertainty generating a kind of internal tension. The bosonic field cannot occupy a singular point in space because doing so would require infinite momentum uncertainty, something nature forbids. This dynamic sets the stage for a self-stabilizing system. Gravity pulls inward. Quantum pressure resists compression. If the mass of the star is too low, the quantum spreading dominates, and the star diffuses away. If the mass is too high, gravity wins and the system may collapse into a black hole, or in some versions, an unstable configuration that decays. But in between lies a delicate sweet spot, where both effects reach equilibrium. That's the boson star. In mathematical terms, this balance arises from solving two sets of coupled equations: the Einstein field equations, which govern gravity, and the Klein-Gordon equation, which governs the scalar field. The solutions show that, under the right conditions, the scalar field can form a stable configuration where its energy is distributed in a spherical, symmetric pattern. The spacetime around it bends gently, and the whole structure hovers in a kind of gravitational limbo. And this balance is remarkably robust. Even when you introduce variations, such as rotation, charge, or self-interaction among the bosons, the system still finds a new equilibrium point. Rotating boson stars, for example, change shape slightly, becoming more oblate due to centrifugal effects, but they can still achieve stability. In some models, these spinning stars can support higher masses than non-rotating ones, thanks to the added angular momentum acting as an extra source of pressure. There's another factor, too, the mass of the bosons themselves. Ultralight bosons create large, diffuse boson stars, potentially the size of galaxies. Heavier bosons produce much more compact configurations, like stellar mass or supermassive boson stars. In either case, the mass of the boson determines how sharply the field can be confined before quantum spreading overwhelms gravity. This adds a natural scale to the system, one that physicists can tweak in simulations to explore different kinds of stars. What emerges is not just a balance, but a spectrum. A landscape of possible boson stars, ranging from light and fuzzy to dense and compact, all stabilized by the same fundamental interplay between curvature and coherence. And unlike neutron stars or white dwarfs, there is no hard surface. No boundary where matter meets vacuum. Boson stars are smooth. The density gradually declines with radius, fading into the cosmic background. This makes them hard to detect, but also makes their internal structure incredibly stable. There are no discontinuities, no cracks, no crusts. Just a continuous field, holding itself together against collapse, pulsing gently like a drumbeat echoing in 4 dimensions. This balance is why boson stars are more than mathematical oddities. They are serious contenders for real astrophysical objects, especially if bosons like axions exist. And it's why they can persist across cosmic timescales. Once formed, they don't burn out. They don't explode. They don't even cool off. They just stay. Suspended in an eternal negotiation between quantum fuzziness and gravitational grip. Imagine a structure that doesn't change unless something disturbs it. A star made not of elements and temperature gradients, but of probability densities and curvature. That's the profound beauty of a boson star. It's a balance written in the deepest language of the universe, 1 part general relativity, 1 part quantum field theory, and entirely alien to our everyday experience. Boson stars, for all their theoretical elegance and structural complexity, share one defining feature that makes them almost mythical in the modern astronomical landscape: they are invisible. Yet despite their ghost-like absence from our telescopes, they could possess enormous mass, comparable to the most massive objects we can see. They could rival neutron stars, mimic black holes, or in some configurations, even anchor the centers of galaxies. They are giants made of silence, casting no light, emitting no heat, and betraying their presence only through the bending of space itself. This invisibility is not a flaw. It's a feature of their very nature. Unlike ordinary stars, boson stars don't undergo fusion. They don't have layers of burning hydrogen or helium radiating photons into the cosmos. They don't glow. They don't flicker. They don't shine. Every visible star we see is, at its heart, a thermonuclear furnace, its mass turned into light. But boson stars skip that process entirely. There is no fusion, no atomic excitation, no mechanism for releasing light. They are made of bosonic fields that, in many theoretical models, are electromagnetically neutral. This means they don't interact with photons at all. Imagine an object the mass of the Sun, or even 1,000,000 times more massive, existing completely dark, invisible across the entire electromagnetic spectrum. No infrared. No X-rays. No radio waves. No visible light. And yet it pulls. It bends spacetime. It warps the path of nearby stars. It shapes galaxies. That's the quiet power of a boson star. So how would we even know such an object exists? We would see its gravitational effects, not its image. Much like dark matter, boson stars would only be detectable indirectly, through the way they influence the motion of surrounding objects. A star orbiting an empty patch of sky, but behaving as though it were circling an unseen mass, might be giving away the presence of a boson star. If the orbit shows signs of curvature without a visible partner, it could be a whisper from one of these quantum structures. In fact, boson stars are such excellent gravitational mimics that, in some scenarios, they could be mistaken for black holes. Their gravity wells could be deep enough to bend light dramatically, causing lensing effects where background galaxies are distorted into arcs or rings. Their gravitational pull could accelerate nearby stars or gas clouds into rapid orbits. In binary systems, a boson star could tug on its partner just like a black hole would, yet when astronomers point their instruments at the location, they might find nothing. What distinguishes them from black holes, however, is critical. They have no event horizon. A black hole is a one-way trap. Once light crosses the event horizon, it cannot escape. But boson stars, despite their density, do not create this kind of terminal boundary. Light can pass through them. Matter can fall in and possibly emerge. They might appear as dense gravitational wells, but they are transparent to many forms of radiation, especially if the bosons themselves don't couple to electromagnetic fields. This transparency adds to their mystery. A boson star could sit in front of a distant light source, like a galaxy or quasar, and lens it without blocking it. Unlike a black hole, which can cast a dark shadow, a boson star might lens and distort light without leaving a telltale silhouette. The result could be a subtle smearing or brightening of light curves, not an absence, but a weird presence, like an invisible hand manipulating the background of space. And then there's their potential mass range. Boson stars are not limited to a narrow class. Depending on the mass of the boson particle and the details of the field configuration, boson stars could range from substellar objects the size of asteroids to supermassive ones millions of times the mass of the Sun. The latter class is particularly compelling, because it opens the possibility that some of the supermassive black holes we've detected, especially those at galactic centers, could actually be supermassive boson stars in disguise. Consider this: we observe quasars, extremely luminous, distant galaxies, with central masses billions of times that of our Sun. These central objects are assumed to be black holes. But we only infer that based on gravitational effects and surrounding emissions. If boson stars can produce similar gravitational signatures, if they can exist in the same mass regime, then perhaps not all of these black holes are as we think. Perhaps some are coherent quantum giants, hiding behind a cloak of darkness not because they trap light, but because they never emit it. There's also the question of motion within galaxies. In the outskirts of galaxies, stars orbit faster than they should based on visible matter. Dark matter is the usual suspect. But what if, sprinkled throughout these galactic halos, were vast, diffuse boson stars? Not dense like their stellar mass cousins, but wide, ghostly blobs of coherent quantum field, contributing gravitationally while remaining undetectable. Their mass might be immense, their radius spanning thousands of light years, their presence never seen, only felt. In the search for these objects, astronomers are beginning to look not just for absences, but for anomalies. Light curves that don't behave. Lensing events that are too smooth. Gravitational wave signals that don't quite match black hole templates. Precision measurements of star clusters orbiting seemingly empty voids. These are the cracks through which the invisible might become known. And yet, boson stars may always remain on the threshold of detectability. They are almost like shadows, not of things, but of possibilities. They represent what can happen when the universe decides not to radiate, not to burn, not to shine, but still to exist, to curve, to matter. They are silent masses in a luminous cosmos. Giants cloaked in transparency. Their invisibility does not make them any less real. In fact, if boson stars do exist, their sheer elusiveness might be the very clue that defines them. Because in a universe filled with noise, the loudest truths may come from what we cannot see, only from what we feel, trace, and infer. Invisible, yet immense. Dark matter. It's one of the great enigmas of modern science, a name we give to something we cannot see, cannot touch, and yet know must be there. Its gravitational fingerprints are all over the universe. Galaxies spin faster than they should. Clusters of galaxies are held together more tightly than visible matter allows. Light bends in space even where nothing visible lurks. It's as though the cosmos is haunted by a massive, invisible presence. And in this silent, unseen theater, boson stars may not just play a role, they might be among the main actors. To understand why boson stars are compelling dark matter candidates, we must first reconsider what dark matter is not. It is not baryonic, made of protons and neutrons like normal atoms. It does not emit or absorb electromagnetic radiation. It's not hot, fast-moving, or easy to scatter. It's cold, invisible, and only interacts through gravity, at least as far as we can tell. Boson stars, as theoretical entities, fit these criteria almost perfectly. Start with their composition. If boson stars are made from fundamental scalar or vector bosons, particles with no charge and no electromagnetic interaction, then they are dark by nature. They would pass through light undisturbed. They wouldn't glow. They wouldn't absorb. And if these bosons are stable and non-interacting, they could have formed in the early universe and persisted for billions of years, just like dark matter. Now add their gravitational influence. Boson stars are massive. They bend space-time. And in certain models, they can be very diffuse, with radii spanning hundreds or thousands of light-years. These extended, low-density boson stars would not resemble compact stellar remnants, but would instead look more like gravitational clouds, invisible spheres that quietly shepherd stars and gas along curving paths. This behavior could account for the flat rotation curves we observe in galaxies, where stars orbit the galactic center at speeds that defy Newtonian predictions based on visible matter alone. If boson stars were sprinkled throughout the galactic halo, they could explain the need for dark matter clumps that don't emit radiation but provide gravitational cohesion. In fact, one class of boson stars, known as fuzzy dark matter models, relies on ultralight scalar particles, like axions with masses around 10 superscript 2 superscript 2 eV. These particles form coherent quantum structures on galactic scales, with de Broglie wavelengths spanning kiloparsecs. The result is a bosonic field that acts like a wave, not a particle, and provides a natural smoothing mechanism that avoids some of the problems of particle-based cold dark matter models, such as the overabundance of small-scale structure. These fuzzy boson star halos would suppress the formation of overly dense subhalos, fixing what cosmologists call the missing satellite problem, and create core density profiles in galaxies instead of sharp central spikes, which aligns better with observations of dwarf galaxies. In this way, boson stars don't just plug into dark matter theory, they solve its puzzles. But there's more. Some theories suggest that entire galaxies could be embedded in a diffuse, coherent bosonic halo, with denser boson stars at their centers. These supermassive boson stars could act like black holes in terms of gravitational influence, but without event horizons. They provide the necessary anchor for stellar orbits, and their lack of surface emissions would make them functionally indistinguishable from black holes, unless probed carefully with gravitational waves or precise lensing data. There's also the intriguing possibility of boson star mergers, events that would release gravitational waves, much like black hole or neutron star collisions. But the waveform, the signal we detect, might be distinct. Because boson stars lack an event horizon and are composed of smooth fields, their mergers might produce longer, more complex wave signals, with echoes and post-merger oscillations that differ from anything seen in black hole physics. Detecting such a signal would be like hearing a language we didn't know existed, proof of a new form of matter. Gravitational wave observatories like LIGO, Virgo, and CAGRA, and future missions like LISA, could one day identify these anomalies. Already, there are events with small deviations from expected waveforms, glitches that spark debate. Could one of them be a boson star masquerading as a black hole? Could some gravitational wave detections be the first whispers of dark matter structures colliding in silence? The idea goes even further. In the early universe, during the post-inflationary period, scalar fields could have naturally fragmented into compact bosonic clumps. These primordial boson stars would be among the oldest structures in existence, forming even before atoms, stars, or galaxies. They would float in the void, accumulating mass slowly, merging, clustering. Some might grow massive enough to seed galaxy formation. Others might remain in the intergalactic dark, invisible but essential. If this were the case, then dark matter might not be a soup of tiny particles but a network of coherent quantum objects, boson stars large and small, linking galaxies in a scaffold of gravity. And because their interactions are so weak, they could have survived the violent collisions of the early universe without destruction, allowing them to remain today as cold, stable ghosts keeping the universe in place. The most tantalizing aspect? If we confirm even one boson star, we may simultaneously solve two of the biggest questions in physics. What other forms of stable matter exist, and what is dark matter made of? It would mean that nature doesn't just hide its mass in particles too small to see, but in structures too subtle to detect. Structures made not of matter as we know it, but of organized quantum fields, whispering across the cosmos in gravitational tones. In that light, boson stars become more than an oddity, they become a key. A key to unlocking not just dark matter, but the deeper architecture of the cosmos itself. Silent, massive, and waiting. In the vast, silent theater of the cosmos, black holes are the ultimate illusionists, objects so dense, so gravitationally intense, that they trap even light. They reveal themselves not by being seen, but by what they prevent us from seeing, the infamous black hole's shadow, a dark void encircled by glowing gas and warped starlight. It's a visual echo of the event horizon, the line beyond which nothing returns. But what if that shadow, that iconic silhouette against the luminous fog of an accretion disk, wasn't always a black hole? What if, in some cases, it was a boson star, a gravitational impersonator capable of casting a nearly identical shadow, without the singularity, without the point of no return? Boson stars, despite their ethereal composition and lack of fusion or surface, can still curve spacetime dramatically. This curvature, if strong enough, can deflect light from background objects just as a black hole would. Light rays that skim near a boson star's core may be bent, delayed, or even looped entirely around the object before emerging toward an observer. This is gravitational lensing, a key prediction of general relativity, and boson stars are masters of it, just as black holes are. Now, here's where it becomes fascinating. Depending on the compactness and mass of the boson star, the light deflection patterns it produces can be nearly indistinguishable from those produced by a black hole. Simulations have shown that under certain conditions, boson stars can create a central region in the lensed image that appears dark, not because light is absorbed or trapped, but because it's so heavily bent that very few rays escape directly toward the observer. This creates a kind of shadow, eerily similar to what we expect from an event horizon. But unlike a black hole's event horizon, this dark core in a boson star is not absolute. It is not a point of no return. There is no horizon. Light may struggle to escape, may take circuitous routes, may even spend extended time orbiting the boson star in a photon sphere, but in theory, it can always emerge. There's always a way out, even if that path is long and convoluted. This leads to one of the most mind-bending possibilities in observational astrophysics. We could already have photographed a boson star and mistaken it for a black hole. When the Event Horizon Telescope released its now famous image of M87, the first black hole ever seen, what we were truly seeing was a ring of radiation bent around a dark core. This was interpreted as the shadow of a supermassive black hole. And most likely it is. But had a boson star been at that location, with the right mass and compactness, the image might have looked almost identical. In fact, one of the key reasons physicists are so excited about high-resolution observations of event horizons is that these could be the only way to distinguish a boson star from a black hole. It's not that boson stars fail to mimic black holes, they do it too well. The distinction becomes a game of precision. Does the light curve behave just slightly differently? Are there subtle photon ring variations? Is there a missing final plunge of infalling matter? One of the most compelling observational differences lies in accretion behavior. Black holes can have hot, bright accretion disks of gas spiraling toward doom. Boson stars, having no hard surface and no event horizon, might absorb gas differently. Some simulations suggest that matter falling toward a boson star might oscillate, slosh around, or even be re-emitted, changing the timing and energy distribution of emissions near the core. These emissions might show unique flickers or echoes not seen near true event horizons. There's also a tantalizing prospect in gravitational wave astronomy. When compact objects merge, be they black holes, neutron stars, or boson stars, the resulting space-time ripples carry information about the merging objects. If a boson star collides with another compact body, the gravitational waveform could deviate from black hole expectations. It might include post-merger echoes, or exhibit a slower damping tail, subtle differences that might let us tell ghosts from gravity trap. Yet the differences are faint, buried in noise, and observational limits. Right now, boson stars sit in a scientific limbo, possible, plausible, but not yet provable. And this is what makes them so compelling. They represent a cosmic doppelganger, an object that could fool even our most advanced instruments. More intriguing still is the fact that some boson star models, especially the ultra-compact ones, can create regions of trapped light orbits very similar to the photon spheres of black holes. In these configurations, light can orbit the boson star multiple times before escaping or falling inward. This produces a bright ring in simulations, eerily reminiscent of the glowing halo seen in black hole imaging. It's a gravitational mirage, a light echo of a shadow that isn't truly a shadow. In a poetic twist, the boson star shows us that the absence of light is not proof of a trap. A dark region may simply be a sign of extreme curvature, not inescapable confinement. And in this way, the cosmos teases us, revealing dark patches that may or may not conceal a singularity, presenting shadows that hint at death, but might actually be whispers of something gentler, something smoother, something quantum. If one day we do find that a supposed black hole is, in fact, a boson star, the consequences will be profound. It will mean that nature found a way to produce enormous, dark, compact objects without breaking physics at a singularity. It will mean that our understanding of matter, gravity, and quantum coherence has only scratched the surface. Until then, every black hole's shadow we capture might be a test. A riddle posed by the universe. Is this the mouth of oblivion, or a masquerade of mass? In the heart of a black hole, the laws of physics shatter. According to general relativity, when enough mass is compressed into a small enough volume, the resulting gravitational pull becomes so intense that it collapses matter to a single, infinitely dense point, the singularity. A place where space and time cease to behave sensibly. A region where density becomes infinite, curvature becomes undefined, and the known equations of physics simply stop working. It's a mathematical cliff, a place our models cannot cross. But what if nature never actually gets there? What if there's a way to have immense gravity, to compress mass to incredible density, without breaking physics? This is where boson stars offer an elegant, almost poetic alternative, because unlike black holes, they may not contain a singularity at all. The idea is as radical as it is beautiful. Where black holes end in paradoxes, boson stars resolve them with subtlety. Instead of a central point where mass is infinitely concentrated, boson stars exhibit a smooth distribution of mass, decreasing gradually from the center outward. There is no sharp edge, no singular center. The bosonic field that comprises the star, whether it's an axion field, a scalar field, or another hypothetical bosonic particle, exists as a coherent, wave-like structure described by continuous functions that never blow up into infinity. This fundamental difference arises because boson stars are not made of hard, discrete particles like atoms or neutrons trying to occupy the same space. Instead, they are made of bosons sharing a single quantum state, a massive wave function extending through space. When compressed by gravity, these wave functions don't clump into a single point. They spread. They resist tight confinement due to quantum pressure, especially in the case of lighter bosons. This non-local nature of the field prevents the infinite compression that leads to a singularity. And that changes everything. In mathematical terms, boson star models do not diverge at the origin. The curvature of spacetime remains finite. The energy density, while peaking at the center, never becomes infinite. The equations remain well-behaved from the outer edges of the star all the way to its core. There is no event horizon, and no hidden singularity beyond it. There's just a smooth, continuous structure, quietly humming with quantum coherence. This also means boson stars don't suffer from the same information paradox that plagues black holes. In a black hole, anything that crosses the event horizon is thought to be lost forever, leading to troubling questions about whether information can be truly destroyed, something quantum mechanics says should never happen. But in a boson star, there's no point of no return, and no central collapse to a singularity. Information might be scrambled, bent, delayed, but not necessarily destroyed. Imagine falling into a boson star. There'd be no dramatic tearing from tidal forces, no horizon to cross. You'd pass through increasing gravitational fields, but in principle, you could come out the other side, though probably mangled by the intense curvature. Still, the physics remains continuous, not catastrophic. The boson star is more like a dense fog of quantum fields than a cosmic pit. This has another profound implication. It suggests that the universe may not be as destructive at its core as we once feared. If boson stars can exist, then perhaps gravitational collapse doesn't always lead to oblivion. Perhaps there are stable endpoints to collapse that don't involve breaking the universe's rulebook. Boson stars offer a kind of cosmic fail-safe, where quantum behavior steps in before gravity becomes too extreme. Some physicists believe this may be the universe's way of avoiding singularities altogether. Instead of tolerating infinite curvature, nature builds alternatives: gravastars, fuzzballs, or boson stars, structures where new physics emerges just before the cliff's edge. These theories are speculative, yes, but they're driven by a need to reconcile general relativity with quantum mechanics. Two theories that should both be true, yet speak very different languages. Boson stars speak both. They use general relativity to curve spacetime, and quantum field theory to fill that space with structure. They are a translation layer, a way of merging two great pillars of physics without forcing either one to collapse. They are, in essence, non-singular solutions, mathematically elegant, physically plausible, and potentially real. And this makes boson stars not just objects of curiosity, but objects of hope. Hope that our universe is not governed by cracks in its foundation. Hope that beneath the infinite densities and paradoxes lies a smoother truth. A truth written not in infinities but in balance. Not in catastrophe, but in coherence. So, while black holes may dominate the popular imagination, boson stars offer a quiet revolution. A challenge to our assumptions. A question whispered into the dark: what if the center of gravity is not a point of destruction, but a wave of order? In the tapestry of the night sky, stars are the brilliant threads that stitch the universe together. They shine because they burn. Atoms fuse in their cores, releasing immense energy as light, heat, and radiation. These luminous signals cross trillions of kilometers to reach our eyes, our telescopes, our detectors. From red dwarfs to blue giants, from supernovae to neutron stars, the cosmos is ablaze with the signatures of nuclear fire. But not all that is massive shines. Boson stars are a class entirely apart. Despite their potentially vast mass and gravitational influence, they are dark by design. They do not emit light, not because they are hidden behind dust or cloaked in gas, but because they lack the very mechanisms that make traditional stars visible. To shine, a star needs atoms, charges, reactions, none of which exist in a boson star. At their core, boson stars are not made of matter in the conventional sense. There are no protons or electrons, no hydrogen undergoing fusion. They are made of bosonic particles, scalar or vector fields, occupying the same quantum state, existing not as point particles bouncing off one another, but as overlapping waves of probability density. These particles can be fundamentally electromagnetically neutral, meaning they do not interact with light at all. Without charges to accelerate, without atoms to excite, without collisions to generate radiation, boson stars are silent in the electromagnetic spectrum. They don't emit X-rays. They don't glow in infrared. They don't pulse in visible light. They are essentially invisible to traditional optical or radio telescopes, which rely on light, or at least some form of electromagnetic signal, to form an image. And it's not just that they're faint. They could be perfectly dark. No emissions. No absorption lines. No spectral footprint to betray their presence. A boson star could sit in the middle of a galactic core or in the halo of a spiral arm, and we might never know, unless we see the way stars curve around it, or light from behind it bends under its gravity. It's as if these stars exist in a shadow realm, detectable only by their effect, not their substance. This feature sets boson stars apart from all other types of stellar objects. White dwarfs shine from residual heat. Neutron stars pulse with radiation. Even black holes, surrounded by accretion disks, blaze with high-energy photons as infalling matter heats up to extreme temperatures. But boson stars don't have surfaces. They don't have crusts. They don't even necessarily have strong magnetic fields. And if they exist in isolation, with no nearby matter to interact with, there's nothing for them to ignite, no radiation to leak out. They are non-radiative structures, cosmic sculptures of pure force. So how do you detect something that doesn't shine? That's one of the greatest challenges of boson star astronomy. Most of our observational tools are blind to them. Even when matter does interact with a boson star, say, gas drifting into its gravitational pull, it may not produce the violent, bright fireworks we associate with accretion onto a neutron star or black hole. The boson star might simply absorb the field slowly, gently, allowing it to merge into its quantum wave function without much radiation. The result is a stealthy gravitational sink, eating without flashing, growing without glowing. There may be subtle clues, though. Some simulations suggest that boson stars might cause flickering or oscillations in nearby matter. As gas passes near the star's gravitational well, it could be modulated by the oscillatory nature of the bosonic field. These fluctuations might generate low-level periodic signals, not from the star itself, but from the interaction zone. Detecting such signals would require extremely sensitive instruments, tuned to the right frequency bands, and a great deal of luck. Another possibility is that boson stars could gravitationally lens background light sources in ways that differ slightly from other dark objects. If a boson star passes in front of a bright galaxy or quasar, it might create a lensing effect that is more symmetric, smoother, or temporally extended than that of a compact black hole. Careful monitoring of microlensing events, like those performed in surveys such as Ogili or Gaia, could reveal these anomalous patterns. Still, these are needle-in-a-haystack searches. And because boson stars do not emit, reflect, or absorb light in any conventional way, they are fundamentally outside the framework of most observational astronomy. It's like trying to find a melody in a soundproof room. Unless you can feel the vibrations, it might as well not be there. This is why boson stars are sometimes referred to as dark stars, not in the mythological sense, but in the physical one. They could be everywhere, silently shaping galaxies, seeding structure in the early universe, haunting the interstellar void, and we wouldn't know. They do not scream their presence into the sky. They whisper into the gravitational field. And yet, paradoxically, their very darkness might be what eventually proves their existence. As our gravitational wave observatories become more refined, as our ability to map space-time curvature improves, we may begin to notice discrepancies. Objects too massive to be invisible, or too invisible to be made of baryonic matter. We may find that some gravitational anomalies aren't caused by unseen planets or rogue black holes, but by quantum stars made of force alone. In a cosmos lit by fire, these stars would be the dark punctuation marks. Not visible, not loud, but necessary for the grammar of the universe to make sense. They do not shine, but their silence may yet speak the loudest truth. Detecting boson stars is like hunting ghosts in a windless night. There's no sound, no reflection, no footprint, and no echo. They slip through the cracks of our most powerful telescopes, shunning the electromagnetic signals that form the foundation of modern astronomy. But the universe leaves no mass unaccounted for, and gravity, silent, universal, inescapable, never lies. This is where the search begins. Boson stars, by their nature, evade direct detection. They don't emit light. They don't interact with electromagnetic radiation. But they do curve spacetime, they do bend light, and they do influence motion. And while traditional methods of observing the universe focus on what shines, a new class of tools, sensitive to curvature itself, are beginning to change the game. One of the first indirect signs that boson stars could exist comes from gravitational lensing, the bending of light as it passes through a gravitational field. If a boson star passes between us and a distant background object, it could cause the light from that object to curve, producing distorted images, magnified brightness, or even multiple images. This phenomenon, called microlensing, has already been used to detect exoplanets and dark stellar remnants. In theory, boson stars could create microlensing events that differ subtly from those caused by other objects. For example, since boson stars can have soft density profiles and lack sharp surfaces, their lensing signatures may be smoother or less abrupt. A standard black hole might create a short, sharp lensing event. A boson star, in contrast, might produce a longer-lasting, symmetric light curve, with a gentler rise and fall. These are subtle effects, but in massive datasets, like those from the Gaia mission or the Vera C. Rubin Observatory, they could stand out. Some researchers are already scanning old microlensing events to see if any match what a boson star would produce. Another indirect method comes from stellar motion. Boson stars, especially the more massive ones, exert significant gravitational influence on their surroundings. If a cluster of stars appears to be orbiting an empty point in space, or behaving as if there's a mass where no light is, astronomers suspect a black hole. But what if, instead of a black hole, it was a boson star? This becomes especially intriguing in galactic centers. Take our own Milky Way. At its heart is an object known as Sagittarius A, long assumed to be a supermassive black hole. But all we truly know is that it has an enormous gravitational influence, millions of solar masses compressed into a tiny region. The stars near it orbit with astonishing speed. Yet it's faint. Its shadow, barely visible. What if that object is not a singularity, but a supermassive boson star, built from ultralight particles that never emit a flicker of light? Simulations of boson star gravitational fields show that they can replicate the orbital paths of nearby stars almost perfectly, up to a point. The slight differences, such as how stars precess, or how close they can approach without falling in, could hold the key. Over decades of observations, scientists are tracking these orbits with extreme precision, hoping that tiny deviations from predicted black hole behavior might point to something stranger, something more quantum. But perhaps the most promising path forward lies in the realm of gravitational waves. When two massive objects spiral toward each other and merge, they create ripples in the fabric of spacetime itself. These waves were first detected by LIGO in 2015, and since then, dozens of black hole and neutron star mergers have been recorded. But not all of them fit expectations perfectly. Boson stars, when they collide, would create unique gravitational wave signatures. Because they lack event horizons, the merger doesn't end in a sudden silence. Instead, the resulting object could oscillate, releasing longer and more complex gravitational wave patterns, so-called echoes, that bounce through the curved spacetime. These echoes might appear milliseconds after the initial merger, and they would be absent in standard black hole collisions. Already, physicists have begun scouring the LIGO-Virgo-Cagra data for these signals. While none have been confirmed, a few events have sparked interest, mergers that don't quite fit the standard templates. The upcoming LISA mission, a space-based gravitational wave detector, promises to be even more sensitive, especially to the low-frequency waves that massive boson star mergers would emit. If LISA detects even one anomaly, it could change everything. And what about boson stars made from ultralight bosons, particles like axions or dark photons? These hypothetical particles are also candidates for dark matter. If they clump together into macroscopic objects, they could form entire dark matter halos or galactic cores. Some theories predict that rotating boson stars could create superradiant instabilities, radiating away energy via gravitational waves as they interact with spinning black holes. These energy leaks could serve as cosmic beacons, revealing the presence of bosonic fields even if no visible matter is involved. There's also pulsar timing, an ultra-precise method of tracking the tick-tick-tick of pulsars across space. If a boson star passes between us and a pulsar, or if a pulsar orbits one, the timing of its signals could be subtly altered. These timing shifts might reveal gravitational irregularities that suggest an unseen, smooth mass object, an object that doesn't radiate, doesn't flare, but bends time itself. And finally, there's the absence of expected phenomena. In regions where we expect a black hole to emit jets or glow from accretion but see nothing, the silence might be telling us something. Perhaps what we're observing is not a failed detection, but a different kind of object entirely. One that doesn't follow the rules of baryonic matter. In short, detecting boson stars means shifting our perspective. We must stop looking for light, and start listening to curves in space-time. We must read between the photons, in the jitter of stars and the rhythm of gravity. It is a new way of observing, a quantum kind of astronomy, where presence is inferred from warped orbits, delayed pulses, bent beams, and ripples in the void. It is astronomy by shadow, by silence, by the echo of mass. And in that silence, boson stars may already be calling. When two black holes collide, the universe shudders, but only for a moment. Their merger produces a brilliant, sharp burst of gravitational waves, a perfect chirp in spacetime, and then, silence. No light. No afterglow. Just a final ring down as the newly formed black hole settles into stillness. It's an elegant, brutal event, a cosmic punctuation mark that ends with an unobservable period. But when two boson stars collide, the outcome could be vastly different, and far more intricate. Because boson stars are not simple points of singularity wrapped in an event horizon. They are extended, coherent quantum fields held together by gravity and quantum pressure. When they merge, their fields don't simply fall into a singularity. They interfere, oscillate, and blend in complex and beautiful ways. So what would happen if two boson stars met in the depths of space, spiraling inward like cosmic dancers? First, the in-spiral phase would appear very similar to that of black holes. From far away, two massive objects orbiting each other under gravity produce familiar gravitational waves, a gradually rising frequency and amplitude as they draw closer. But even here, subtle differences might emerge. Because boson stars lack event horizons and can be more diffuse than black holes, the in-spiral could begin slightly differently. The stars might deform each other, creating tidal distortions and resonance effects not seen in black hole binaries. Next comes the merger phase, and here is where the truly exotic physics might emerge. Instead of the abrupt coalescence and ring down that define black hole collisions, boson star mergers might produce a complex series of overlapping waveforms, a swirling quantum ballet. As the stars collide, their bosonic fields interfere. They may not collapse immediately. Instead, their mass energy could slosh around violently, forming a transient, overmassive boson star that oscillates intensely before either settling into a stable configuration or, if pushed beyond a critical limit, collapsing into a black hole. But if the final state remains a stable boson star, then the post-merger gravitational waves would look radically different from the damped sine wave of a black hole's ring out. These would feature echoes, a series of repeating, slowly decaying wave bursts that reflect the internal oscillations of the star's quantum field. Some theoretical models suggest these echoes could be evenly spaced, like a drum slowly quieting, or irregular, if the post-merger remnant is in a chaotic intermediate state. These gravitational echoes are more than a curiosity, they're a signature. A calling card that says, "This was not a black hole." They arise from the internal structure of the boson star. The lack of an event horizon allows space-time curvature to rebound, reflect, and reverberate in ways impossible within a true black hole. In other words, boson stars have memory, and that memory is etched into the waveform long after the initial merger is done. In contrast, neutron star mergers also produce light, kilonovae, gamma-ray bursts, electromagnetic counterparts across the spectrum. Boson star mergers might be completely dark, or emit strange, weak signals unlike anything we've observed. They could produce no light at all, or emit something totally unfamiliar, depending on how the bosonic fields interact with any surrounding matter. Some models even speculate that the collision of rotating boson stars might lead to the formation of non-axisymmetric remnants, lumpy, rotating structures that radiate continuous gravitational waves for long durations after the merger. These persistent wave sources could be detectable by future observatories, and would stand out like beacons in the gravitational sky. One especially tantalizing possibility is the formation of solitonic structures after the merger, localized, long-lived energy packets in the bosonic field that persist for enormous timescales. These structures would radiate very faintly, or not at all, except gravitationally. If such remnants exist, they might even resemble ultralight bosonic halos, dark matter cores that haunt galaxies without ever shining. And then there's the prospect of mixed mergers, a black hole colliding with a boson star. Such an event would be even stranger. The boson star would not simply fall in like a rock. Its extended field would stretch, deform, and wrap around the black hole. Some of it might be absorbed, while the rest oscillates, forming gravitational wave signals that are distinct from binary black hole mergers. The gravitational waveform would include asymmetries, tidal disruptions, and perhaps even the partial destruction of the boson star's quantum structure. These events are within the reach of our current instruments, barely. LIGO and Virgo have already detected mergers that stretch the boundaries of known models. Some of them, like GW190521, involved massive objects that may be too large for traditional stellar collapse, raising the possibility that exotic objects like boson stars could be involved. Researchers are actively working on creating template banks, pre-computed waveforms for various merger types, to match against incoming data. If a boson star merger occurred, and we didn't have the right template, we might have already detected it, and dismissed it as noise. Looking ahead, next-generation detectors will sharpen our ears. LISA, in space, will pick up the lower frequencies associated with supermassive boson star mergers. Einstein Telescope and Cosmic Explorer will reach deeper into the universe, detecting fainter, more distant events with unprecedented clarity. These instruments could finally let us distinguish the subtle heartbeat of a boson star from the violent clang of a black hole. In this gravitational symphony, boson stars are the long notes, the low, drawn-out hums, the complex rhythms that echo through curved spacetime, refusing to go silent. Their collisions are not final acts, but prolonged dialogues, waves speaking across light years, telling us that something different happened here. And if we learn to listen more closely, we may find that the universe has already been humming with boson star mergers all along. We just needed to hear what silence really sounds like. Black holes have long dominated our imagination as the ultimate cosmic enigmas, objects so dense that nothing, not even light, can escape their grip. From the monstrous M87 image by the Event Horizon Telescope to the dozen-odd mergers recorded by LIGO and Virgo, we've catalogued many objects whose gravitational behavior screams black hole. But what if some of them are not what they seem? What if lurking behind the label of black hole is something much stranger, a boson star in disguise? This isn't just idle speculation. It's a legitimate question posed by physicists working at the intersection of general relativity and quantum field theory. Boson stars, if compact enough, can imitate black holes in mass, gravitational lensing, orbital influence, and even merger signatures. They are, in many ways, astrophysics' great imposters. Let's begin with the basics. How do we usually determine that something is a black hole? In practice, we can't see a black hole directly. We detect it indirectly through the way it influences its environment. We infer its mass from the orbits of nearby stars. We detect X-rays from the hot gas falling toward it. We watch for the shadow it casts against the glowing accretion disk around it. But none of these observations confirm the presence of an event horizon, that invisible, one-way boundary that defines a black hole. That's the catch. Every single black hole candidate to date is inferred, not confirmed. And the signatures we use to label them as black holes can often be reproduced by boson stars under the right conditions. Take the famous Sagittarius A, the supermassive object at the center of our Milky Way. It holds over 4 million times the mass of the Sun, yet occupies a volume smaller than our solar system. Stars like S2 whip around it with immense speed. From this, we conclude, black hole. But this conclusion assumes there's no alternative that could house that much mass in such a small region without collapsing into a singularity. Boson stars offer exactly that alternative. Theoretical models show that boson stars composed of ultralight bosons, such as axions or dilatons, could achieve extreme compactness without forming an event horizon. These particles, with masses trillions of times smaller than that of an electron, can form stable, massive, and dense configurations thanks to the balance between gravitational attraction and quantum dispersion. Under specific configurations, particularly when self-interactions between the bosons are introduced, a boson star can become almost indistinguishable from a black hole in terms of gravitational influence. The differences, however, are subtle and crucial. For instance, boson stars lack a singularity and an event horizon. This means they might interact differently with infalling matter. While a black hole devours everything past its horizon with no trace, a boson star might absorb matter slowly, radiate faint signals, or even eject some material. The result would be a slightly different accretion behavior, possibly leading to dimmer X-ray emissions, less violent flaring, or periodic variabilities due to oscillations within the bosonic field. Yet even this behavior isn't always clearly distinct. In some simulations, especially with very compact boson stars, the infalling matter behaves almost exactly as it would with a black hole. So unless we're looking extremely closely, tracking every flicker and fluctuation, we might miss the clues entirely. And then there's gravitational lensing. Light bending around a boson star can produce the same shadow-like effect we associate with a black hole. The Event Horizon Telescope's image of M87 showed a ring of light surrounding a dark core. But that dark region isn't a photograph of an event horizon, it's an image of light being bent and distorted around a compact mass. Some models of boson stars can produce similar photon spheres, or regions where light orbits before escaping. The result? A shadow that looks just right. So again, how do we know? The answer, at present, is, we don't, at least, not for sure. Many physicists now believe that some fraction of what we currently classify as black holes could actually be boson stars, especially those in the intermediate mass range, where observations are less precise. It's less likely that all black holes are imposters, particularly the ones with extremely well-behaved merger signatures, but it's entirely possible that some aren't what they seem. In fact, several merger events detected by LIGO and Virgo, like GW190521, an unusually massive and short-lived signal, have prompted speculation about non-standard objects being involved. The final remnant of that event, if it was a black hole, had a mass that sits awkwardly in the mass gap between stellar and supermassive black holes. Some have hypothesized that it may have involved exotic matter, or even boson stars. Future observations may help us peel back the mask. Gravitational wave detectors like LISA will be able to catch the lower frequency signals of massive binary systems, potentially spotting the subtle differences in waveforms that distinguish boson-star mergers. These differences could include longer ringdowns, post-merger echoes, or frequencies that deviate from black hole models. Similarly, the next generation of VLBI, Very Long Baseline Interferometry imaging, what produced the M87 image, will offer higher resolution snapshots of black hole candidates. If any of them show features inconsistent with event horizon behavior, such as flickering inside the supposed shadow, or light emerging from within, it would raise major questions. And if we discover that even one known black hole candidate is actually a boson star, it would be a revolution. It would mean that some regions of space that appear dead and collapsed are actually alive with quantum coherence. It would confirm the existence of a new form of matter. And it would signal that the universe has more than one way to hide mass, and more than one way to fool us. So yes, we could be mistaking boson stars for black holes. And maybe, just maybe, we already have. Beyond the familiar world of electrons, protons, and photons, beyond the matter that forms you, me, stars, and galaxies, lurks a speculative but tantalizing frontier of physics, a realm filled with particles we've never seen, but which might fill the universe. Chief among these ghostly candidates are axions, the hypothetical bosons that could form the very foundation of boson stars. First proposed in the late 1970s as a solution to a subtle problem in quantum chromodynamics, QCD, the theory that governs how quarks bind into protons and neutrons, axions were born not from cosmology, but from a mathematical symmetry puzzle. The problem was this: QCD predicts a certain kind of charge parity, CP, violation that we don't observe in experiments. In other words, something seems to be finely tuned in nature so that protons and neutrons behave more symmetrically than expected. Physicists Roberto Pecchiai and Helen Quinn proposed a new symmetry to explain this, and shortly afterward, Frank Wilczek and Steven Weinberg showed that this symmetry implied the existence of a new particle, the axion. At first, axions were assumed to be relatively heavy, and thus easy to detect. But as experiments failed to find them, theorists realized they could be ultralight, with masses as low as electron volts. To put that into perspective, an electron has a mass of roughly 500,000 electron volts. An axion could be so light that its wavelength stretches across kilometers, or even entire galaxies. Why does this matter for boson stars? Because boson stars are not made of normal matter. They are composed entirely of bosonic fields, particles that can stack into the same quantum state and behave as a single, unified wave function. The lighter the boson, the larger the resulting star can be. This is why ultralight bosons, like axions, are ideal candidates for building such objects. A boson star made of axions wouldn't be the size of a neutron star. It could be the size of a planet, or even a galaxy, depending on the particle's mass. Moreover, axions are non-interacting with light, or at least minimally interacting, which fits perfectly with the nature of boson stars. If axions exist, they could clump together gravitationally without emitting or absorbing radiation, forming stable, compact configurations. These objects wouldn't shine. They wouldn't scatter light. They would be, effectively, dark stars. And therein lies the connection to dark matter. For decades, physicists have been searching for what makes up the 85% of the universe's matter that doesn't emit light, dark matter. Axions are one of the top contenders. If they exist in abundance, they could form vast halos around galaxies, explaining the strange rotational curves we see in spiral galaxies. But more than that, under the right conditions, axions could condense into gravitationally bound clumps, axion stars, or more generally, boson stars. The idea is that these particles, due to their bosonic nature, could undergo a process similar to Bose-Einstein condensation on a cosmic scale. If the temperature is low enough and the density is right, axions could fall into the same quantum state and form a coherent object, a boson star that behaves more like a wave than a solid. And axions are not alone. Other hypothetical bosons are being explored too. One popular class includes dark photons, which are like ordinary photons but with a small mass and no interaction with normal matter. Another includes dilatons and moduli, which emerge in certain versions of string theory and extra-dimensional models. These particles could have a wide range of masses and self-interaction strengths, potentially leading to a diverse zoo of boson stars, each with different stability, size, and compactness. The properties of the boson, its mass, its self-interaction, whether it's charged or neutral, determine what kind of boson star can be built. For example, non-interacting, ultralight bosons form very large, diffuse boson stars, ideal as dark matter halos. Self-interacting bosons allow for more compact, stable configurations, resembling neutron stars or black holes in mass and size. Charged bosons, hypothetical, could lead to even more exotic structures with electromagnetic interactions, though these are more speculative. Some models even explore multifield boson stars, where two or more types of bosons interact and stabilize each other, leading to even richer dynamics. Think of it like layers of different quantum fields, each oscillating at different frequencies but bound together gravitationally, cosmic orchestras rather than soloists. This makes the search for axions and other ultralight bosons not just a particle physics quest, but a cosmological one. If we can confirm that these particles exist, we not only solve one of the biggest open questions in physics, the nature of dark matter, but we also open the door to a new class of astrophysical objects, boson stars made of pure force, held together by nothing more than the rules of quantum fields and the pull of gravity. Axions could be everywhere, in the halos of galaxies, in the early universe, even right here on Earth as a pervasive background field. And if we can learn to detect them, through laboratory experiments like ADMEX, Casper, or future high-sensitivity detectors, we might begin to uncover the material that makes up the invisible architecture of the cosmos. So when we speak of boson stars, we're really speaking of a grand convergence between particle physics, astrophysics, and cosmology. These aren't just theoretical novelties. They could be built from the very particles that shape the unseen skeleton of our universe. And in the quiet, vast dark between the stars, these ultralight particles may already be gathering, forming structures we've never seen, never touched, but which still shape everything. The cores of galaxies hold some of the most extreme objects we've ever observed, supermassive black holes with millions or even billions of times the mass of our Sun. They anchor galactic spirals, devour stars, and power some of the brightest phenomena in the universe, like quasars and relativistic jets. But for all their influence, these behemoths remain shrouded in mystery. We can't peer past their supposed event horizons. We can't see what's inside. All we truly know is that something massive and dark sits in those cores, warping space-time, commanding stars, and drinking light. And that raises a thrilling question. What if not all of them are black holes? What if some are supermassive boson stars? This idea, once fringe, has become increasingly compelling in light of the strange properties we observe in galactic centers and the flexibility boson stars offer in terms of structure and behavior. The core concept hinges on a simple fact: gravity only cares about mass and energy, not what's providing it. If a boson star can reach the same mass and compactness as a black hole, then in many ways, it could exert the same influence, without needing an event horizon or singularity. Let's look at some of the evidence that opens the door to this idea. First, consider Sagittarius A, the object at the heart of the Milky Way. Decades of observations have shown that stars orbit it with speeds and trajectories that imply a central mass of over 4 million suns. And yet, Sagittarius A is surprisingly dim. For something with access to so much surrounding gas and dust, it emits far less radiation than expected from a typical accreting black hole. Its behavior has puzzled astronomers for years: quiet when it should be ravenous, calm when it should be chaotic. Could this subdued nature be because it's not a black hole at all? Could it be a boson star, massive, compact, but without an event horizon to swallow and heat in falling matter? In theoretical models, a supermassive boson star made of ultralight bosons could replicate many of the gravitational effects of a black hole. The mass could be concentrated enough to match stellar orbits, and the absence of a hard surface or horizon would allow for unusual interactions with matter. For example, gas falling in wouldn't necessarily be heated and radiated away. it might merge gently into the bosonic field. This could explain why Sagittarius A doesn't flare like other galactic nuclei. Even more striking is the behavior of quasars, hyperluminous galactic cores thought to be powered by supermassive black holes devouring matter at an incredible rate. These structures can outshine entire galaxies, yet some quasars exhibit unusual time delays, asymmetries, or emission features that don't fully match black hole accretion models. If boson stars, especially rotating or multi-field ones, are involved, they might produce gravitational effects that modify how radiation is emitted or delayed, leading to these anomalies. Let's talk about size and structure. Boson stars have no hard surface, no crust. Their size is determined by the mass of the bosons they're made from. The lighter the particle, the larger the object can be. This means that boson stars made from ultralight particles like axions could theoretically span regions as vast as the orbits of planets, even while possessing immense mass. Unlike black holes, their density isn't infinite. Instead, it tapers smoothly from the center outward, a characteristic that can lead to distinct lensing patterns and internal dynamics. A rotating supermassive boson star might also avoid forming an ergosphere or a singularity, features present in curved black holes. Yet its external gravitational field could still resemble that of a rotating black hole, especially if the star is highly compact. This again makes it an effective gravitational mimic, an object that, from the outside, behaves like a black hole, but whose internal physics is profoundly different. Another possibility is that some of these black holes are hybrid objects. For instance, a boson star with a small black hole at the center, or a core collapse remnant that became a boson star instead of forming a singularity. In some models, boson stars can stabilize matter that would otherwise collapse completely, creating objects with a core of condensed bosonic field surrounded by a thin shell of normal matter or radiation. This could, in theory, explain some peculiar objects that seem too massive for a neutron star, too dim for a black hole, and yet too compact to be anything else. Let's also consider the broader cosmological implications. If boson stars can be supermassive, then they may have formed very early in the universe's history, before the first stars and galaxies. In fact, because they don't rely on fusion or normal matter, they could have condensed directly from fluctuations in the primordial bosonic fields that permeated the early universe. These primordial boson stars could have acted as seeds for galaxy formation, providing the gravitational anchors around which matter collected. This is especially relevant when we consider how quickly supermassive black holes seem to have formed in the early universe. Some quasars have been observed just 700 million years after the Big Bang, with black holes already a billion solar masses large. Traditional models struggle to explain how stellar remnants could grow that fast via accretion alone. But boson stars don't need a stellar origin. They could form whole and massive from the start, bypassing the need for long growth periods. They could even merge with each other early on, building mass faster than any black hole could. Finally, the existence of supermassive boson stars would rewrite our understanding of galactic cores and cosmic structure. We've assumed for decades that black holes are the engines behind galaxy dynamics, jet production, and high-energy emissions. But boson stars could accomplish some of the same feats through different mechanisms. Rotating boson stars could, in theory, create frame dragging and energy extraction effects similar to those around spinning black holes, without requiring a horizon or singularity. Moreover, their very presence could solve puzzles in galactic rotation curves, core density profiles, and even dark matter distributions. Instead of separate solutions to each anomaly, black holes here, dark matter there, exotic fields elsewhere, supermassive boson stars offer a unified answer. A single class of quantum objects that explain mass, structure, and behavior all at once. Of course, we haven't proven their existence yet. But we're getting closer. Future gravitational wave detections of supermassive object mergers, high-resolution imaging of galactic cores, and axion detection experiments could one day converge on the same truth: that what we thought were the darkest pits of the universe are actually filled with the purest expressions of quantum structure. Not holes, but stars. Not singularities, but waves. Not silence, but coherence. And when we finally see one clearly, when the veil lifts, we may discover that the cosmos has been whispering their presence all along, hidden in plain gravitational sight. The universe is littered with objects defined by limits, boundaries where nature seems to say, "No farther." Nowhere is this more evident than in the concept of the event horizon, the invisible boundary around the black hole beyond which nothing, not even light, can return. Once something crosses that threshold, it is gone forever, hidden behind a veil of infinite gravity and unknown physics. But boson stars challenge this limit. They present a vision of the cosmos where extreme compactness doesn't require an event horizon, where mass can concentrate without collapsing into a singularity, and where gravitational forces grow strong, but not absolute. In essence, they suggest that nature may have other ways of building compact, massive objects, ways that don't end in a horizon. Let's explore how that's possible. To understand why boson stars avoid event horizons, we need to look at what creates one in the first place. In general relativity, an event horizon forms when mass collapses past the critical density, such that escape velocity from the surface exceeds the speed of light. This usually happens when there's nothing to stop the gravitational pull from overwhelming all other forces. In neutron stars, degeneracy pressure from neutrons holds gravity at bay until a certain mass is reached. Beyond that, collapse becomes inevitable, and a black hole is born. But boson stars play by different rules. They are composed not of atoms, not of protons or neutrons, but of bosonic quantum fields, particles like axions or scalar bosons that obey Bose-Einstein statistics. These particles can all occupy the same quantum state, effectively becoming a single macroscopic wave function. And crucially, this wave function has its own internal dynamics, including quantum pressure and field gradients that resist compression. So even as gravity pulls the bosons inward, these quantum effects push back. The result is an equilibrium, not between particles repelling each other like in ordinary matter, but between the tendency of the field to disperse and gravity's drive to collapse it. The star stabilizes. Not through heat or fusion or degeneracy pressure, but through the structure of the wave function itself. It's like a musical note suspended in space, coherent, self-contained, and oscillating in harmony. This allows boson stars to become incredibly compact, denser than neutron stars, potentially almost as compact as black holes, without triggering horizon formation. In fact, the degree of compactness depends on the mass of the bosons and whether they interact with one another. Non-interacting bosons form diffuse stars with low central densities. But introduce self-interactions, and suddenly you can support far more mass in a much smaller volume. Some models predict that boson stars with strong self-interaction terms could mimic black holes so closely that only extremely precise observations would distinguish them. But there's always one crucial difference: no point of no return. In a boson star, space remains open. You could, in principle, send a probe toward the center, and it would not hit a horizon. It would encounter gradually increasing densities, but always within a well-defined geometry. Light might be bent dramatically, delayed, or redshifted, but it wouldn't be trapped forever. This has profound consequences. First, it means boson stars don't harbor singularities. There's no breakdown of physics at the core. The quantum field is smooth. There's no infinite density, no infinite curvature. The very concept of a center may not apply in the way it does for classical objects. What lies within might be better described as a standing wave of probability, a quantum fog, rather than a solid point. Second, it means boson stars can emit signals from within what would otherwise be the event horizon in a black hole. This could lead to observable effects, strange gravitational lensing, echoes in gravitational waves, or delayed light pulses that bounce off deep regions of curved spacetime and eventually escape. It opens the door to physics beyond the veil, places where we can peer deeper than we ever could into a black hole. Third, it offers a compelling alternative endpoint to collapse. In our current understanding, massive stars above a certain mass threshold must collapse into black holes, as nothing can resist the force. But if the matter transitions into a bosonic state, either by converting into scalar particles or coupling with pre-existing fields, it could condense into a boson star instead. This could mean the universe contains many more compact objects than we realize, with some escaping black hole fate entirely. Even more intriguingly, theoretical work has suggested that quantum gravity effects could favor boson stars over black holes in certain regimes. For example, in loop quantum gravity or string theory-inspired models, singularities are forbidden or smoothed out. Boson stars might naturally arise as the true quantum-corrected objects, where the classical notion of a black hole breaks down and is replaced by a field-based structure. Some researchers even go further, proposing that the information paradox, the conundrum of whether information is lost inside black holes, could be resolved if black holes are really boson stars in disguise. Since boson stars lack horizons, information wouldn't vanish. It would be encoded in the field, in the slow oscillations, or in the faint signals that eventually leak out. This makes boson stars not just a black hole alternative, but a window into quantum gravity itself. They offer a model for ultradense, horizonless, stable objects that obey both Einstein's equations and quantum principles. A kind of bridge between the continuous geometry of spacetime and the discrete behavior of quantum fields. To sum it up, boson stars can become immensely compact without becoming black holes because they're governed not by collisions and fermionic pressure, but by coherent field dynamics and quantum interference. Their densities can soar, their gravity can stretch spacetime, but the horizon remains just out of reach. They are the stars that refuse to vanish, the shadows without singularities, the densest objects you can imagine, without ever falling past the point of no return. In that sense, they challenge one of our deepest assumptions about the cosmos, that collapse must end in silence. Boson stars suggest otherwise. They show us that collapse can end in coherence. That gravity, given the right partner in the quantum world, doesn't need to destroy. It can create, and sustain, a new kind of structure altogether. Rotation is one of the most fundamental properties in the universe. From galaxies spinning slowly over billions of years to neutron stars rotating hundreds of times per second, angular momentum is a key ingredient in shaping celestial bodies. But when it comes to boson stars, these ghostly, gravity-bound waves of quantum matter, rotation becomes even stranger, more elegant, and possibly more revealing. In ordinary stars and compact objects like neutron stars or black holes, rotation flattens the object at the poles and bulges it at the equator. This is known as oblateness, and it's a well-understood consequence of centrifugal force resisting inward gravitational pull. For black holes, especially curved black holes, rotation alters the spacetime around them, producing effects like frame dragging and the ergosphere, a region where spacetime itself is dragged along with the rotation. But boson stars are different. They are not made of solid matter or even hot gas. They are composed of a complex scalar field, a wave-like structure with no fixed surface. So when a boson star rotates, it doesn't spin like a solid ball. Instead, its entire quantum field begins to twist and swirl, creating a structure more akin to a rotating cloud of probability than a spinning rock. This gives rise to a class of objects known as rotating boson stars or spinning scalar field solitons. These are among the most exotic configurations predicted by general relativity coupled with field theory. Instead of rotating uniformly like a planet or star, the field exhibits quantized angular momentum, discrete, allowed values of spin determined by the number of times the field winds around its center. This quantization arises because boson stars are governed by wave functions, and just like electrons in atoms, their angular momentum is restricted to integer multiples of a fundamental constant. In effect, a rotating boson star has a winding number that describes how its phase rotates in space. The simplest spinning boson stars have winding number, and more complex ones can go higher. Now, what does this rotation do to the star's structure? First and foremost, it stabilizes certain configurations. In non-rotating boson stars, there's a maximum mass above which the object collapses or disperses. But when rotation is introduced, the centrifugal force can support additional mass, meaning spinning boson stars can be heavier and larger than their static counterparts. In fact, rotation allows the star to exist in a broader range of parameter space, possibly making it more viable as a real astrophysical object. Second, rotation changes the shape of the boson star. Instead of being spherically symmetric, spinning boson stars become toroidal, donut-shaped, with the peak of the scalar field density forming a ring around the central axis. The center may be nearly empty or only weakly dense, depending on the configuration. In extreme cases, the central hole may become a true vacuum, while the scalar field forms a dense torus rotating around it. This toroidal structure leads to gravitational properties that are significantly different from those of a non-rotating star. Light paths near such an object would be bent in complex ways, producing distinctive lensing signatures. If imaged like M87, a rotating boson star might show asymmetric light rings, lensing artifacts, or brightness patterns inconsistent with classical black holes. In addition to shape, spin also affects stability. Rotating boson stars can either be long-lived or unstable, depending on their mass, spin, and the nature of the boson. Some configurations slowly radiate away energy via gravitational waves and settle into non-rotating states, while others might survive indefinitely, especially if they're in a stable energy minimum. Introducing self-interactions among the bosons can further stabilize these configurations, preventing collapse or dispersion. Furthermore, spin enables the possibility of vortex formation, akin to what is seen in superfluids and Bose-Einstein condensates. In rotating superfluid helium, for example, the fluid forms discrete vortices, tiny, quantized whirlpools that carry angular momentum. The same may happen in boson stars. Under certain conditions, the scalar field could develop internal vortices, localized regions where the phase of the wave function wraps around a point. These vortices could play a role in stabilizing the spin and shaping the dynamics of the star. Some researchers have even proposed that vortical boson stars could exist with multiple vortex cores, each behaving like a mini boson star within the larger object. Imagine a spinning celestial body not with one dense center, but several, all orbiting a shared axis in a coherent field, a true quantum storm in space. Now, spin doesn't just affect internal structure. It also changes how a boson star behaves in binary systems and collisions. A spinning boson star merging with another, whether rotating or not, would produce a gravitational wave signature influenced by its angular momentum. The asymmetry, the delays in collapse, the interference of fields, all of it would imprint on the waveform in ways that differ from merging black holes. And since boson stars lack an event horizon, rotating ones might produce persistent gravitational echoes, ringing patterns that continue far longer than in black hole mergers. These could be detected by gravitational wave observatories, serving as potential fingerprints of rotating boson stars. Rotation may also allow boson stars to emit jets or radiation in limited scenarios. While they don't produce light through fusion, interactions at the surface or with infalling matter, especially if spin generates magnetic-like effects in the field, could lead to low-energy emissions or quantum instabilities. The presence of spin might even mimic features of accretion disks, fooling observers into thinking they're looking at a traditional black hole system. And then there's the matter of frame dragging. In general relativity, a rotating mass causes nearby spacetime to swirl along with it, a phenomenon called frame dragging. Around spinning boson stars, this effect still occurs, though its intensity and spatial extent depend on the mass and spin of the star. This means that orbiting objects, photons, or gravitational waves would be subtly affected by the star's rotation, a detectable feature if the resolution of instruments improves. In short, spin elevates boson stars from strange to stunningly complex. They stop being mere spherical solutions and become rotating, toroidal, quantized objects, not solid, not gaseous, but coherent states of a field that carries mass, angular momentum, and perhaps even charge. They become not just alternatives to black holes, but entities with distinct identities, shaped by the peculiar rules of the quantum world. In these rotating configurations, we see a full expression of the boson star's potential, a star without fusion, without atoms, without light, but with structure, motion, and balance. An object that spins like a galaxy, holds itself together like a wave, and exists right at the edge of what's possible in our universe. In the first few moments after the Big Bang, The universe was a swirling, chaotic sea of fundamental particles, quantum fields, and incomprehensibly high energies. Time itself had barely begun, and yet, in that raw furnace of creation, the seeds of every galaxy, star, and planet were sown, not just in the form of baryons or radiation, but possibly in the form of something much stranger. Among the most fascinating possibilities is that boson stars may have formed in those very first seconds, long before atoms, long before fusion, long before the cosmic web began to stretch across space. These hypothetical structures, primordial boson stars, could represent the earliest organized clumps of mass in the universe, born not from cooling gas or gravitational collapse, but from the direct interplay of quantum fields and gravity. To understand how, we need to revisit what the early universe looked like. Immediately after the Big Bang, the universe was extremely hot and dense, filled with rapidly expanding energy fields. Matter and antimatter were constantly being created and annihilated. As the universe cooled during its rapid expansion, particularly during inflation, an exponential growth phase that smoothed out the cosmos, tiny quantum fluctuations were stretched to cosmic scales. These fluctuations became the seeds for structure, laying the groundwork for galaxy formation billions of years later. But what if some of these fluctuations were in bosonic fields? If axions or other ultralight bosons existed in the early universe, and many theories like string theory or extensions of the Standard Model predict that they did, then it's entirely plausible that some regions of the universe became locally overdense in these fields. In those overdense pockets, the bosonic field might have undergone gravitational collapse not into singularities, but into coherent field configurations, boson stars. This kind of collapse would be governed not by pressure and fusion but by the coherence and self-interaction of the field itself. Where traditional matter clumps through particle collisions and thermal cooling, bosonic fields can self-bind through gravity and field gradients, especially when the field is nearly homogeneous over large volumes. Exactly the kind of conditions that inflation might leave behind. These primordial boson stars would be formless at first, nothing more than standing waves of a scalar field bound together by gravity. They wouldn't emit light. They wouldn't burn. But they would hold mass, warp spacetime, and persist, potentially from the first fractions of a second until today. Some theories go even further, suggesting that primordial boson stars could be as abundant as dark matter halos, acting as building blocks for galactic formation. In this view, before the first atoms formed, before baryons could collapse under their own weight, the universe already had massive clumps of gravitational potential, silent, invisible boson stars scattered across space, subtly attracting matter toward them and speeding up structure formation. This might help solve a long-standing puzzle in cosmology. How did supermassive black holes appear so early in the universe? Some quasars, observed at redshifts corresponding to less than 1 billion years after the Big Bang, already host black holes billions of times more massive than our Sun. Traditional models struggle to explain how stars could form, collapse, and accrete enough matter in so little time. But if boson stars formed early, and especially if they were supermassive from the start, they could act as seeds for galaxies, pulling in baryonic matter and triggering rapid star formation around them. Moreover, boson stars might help resolve the core-cusp problem in dark matter simulations. Cold dark matter models often predict that dark matter halos should have steep density spikes, or cusps, at their centers. Yet observations suggest that many galaxies have flat density cores instead. If some of these cores are smooth boson stars rather than particle swarms, it could naturally explain the discrepancy. Boson stars also offer insight into the dark age of the universe, the period after recombination, when photons decoupled from matter but stars had not yet formed. This era is largely invisible to telescopes, but boson stars, if they existed, would still be influencing the universe's expansion and structure through gravity. They could be subtle architects of cosmic evolution, leaving their mark not in light, but in the gravitational scaffolding of everything that followed. In some models, oscillons, localized oscillating field configurations that are not fully stable but can live for extended periods, may also have played a role. These could have emerged from the same scalar fields and later decayed into boson stars or other compact structures. If boson stars were part of this early population, they may have interacted with radiation, matter, and even each other, forming early networks of gravitational potential that shaped the behavior of larger-scale structures. Another fascinating aspect is the possibility of boson star binaries forming early. Two boson stars orbiting each other from the primordial soup might have survived billions of years, spiraling together, and eventually merging in the current era, producing gravitational wave signals very different from black hole mergers. If detected, such a signature would be a literal time capsule from the Big Bang. Even the cosmic microwave background CMB might hold faint echoes of boson star formation. Anomalies in the distribution of temperature fluctuations, especially if correlated with large-scale structure surveys, could hint at early mass concentrations inconsistent with standard dark matter models. These could be subtle, non-luminous hints of field-based clumps born long before the first light. Today, boson stars born in the early universe would be dark, quiet, and elusive, wandering the vast spaces between stars and galaxies, or nestled in galactic halos, influencing the motion of stars and gas through their gravitational pull. They may even be mistaken for black holes or massive dark matter halos, their true nature hidden beneath layers of assumption. But if we could prove their existence, it would open an entirely new window into the origins of structure in the cosmos. It would suggest that not all mass came from fusion, or collapse, or cooling. Some came from the quantum echoes of the Big Bang itself, bosonic fields coalescing into stability not through destruction, but through coherence, symmetry, and gravity. In this view, boson stars are not just modern curiosities or black hole mimics. They are primordial relics, surviving testaments to the strange, field-driven physics that govern the infant universe. And though they do not shine, they may be the first stars the cosmos ever knew. Could boson stars still be out there, hiding in plain sight, silent sentinels in the dark? It's a question that echoes louder with every new anomaly we find in the cosmos. As we map the structure of galaxies with greater precision, as we observe stars behaving in ways that subtly defy expectation, and as we refine our measurements of gravitational forces on cosmic scales, one possibility keeps resurfacing: that something massive, dark, and entirely unlike anything we've ever touched is exerting influence from the shadows. And boson stars, with their ethereal makeup and gravitational strength, could be the culprits. Let's begin with the dark matter halos of galaxies. According to standard cosmology, every galaxy is surrounded by an enormous, invisible sphere of dark matter, more massive than all the stars within it, and yet totally transparent to light. These halos are what keep galaxies from flying apart. They provide the extra gravity needed to explain why stars in the outer edges of galaxies orbit faster than they should, given the visible matter. But there's a problem. While dark matter explains a lot, we don't know what it is. And that leaves room for ideas like boson stars embedded in halos, or in some cases, making up the halos themselves. Ultralight bosons, like axions or other scalar particles predicted in many extensions of the Standard Model, can form enormous, diffuse boson stars that match the shape and size of galactic halos. These structures, known in some models as fuzzy dark matter halos, don't behave like clumps of particles. They behave like a smooth, oscillating field. The quantum pressure of the bosonic field smooths out the inner regions of the halo, naturally preventing the formation of dense central cusps that standard cold dark matter predicts but that real galaxies don't show. This is one of the strongest clues that bosonic structures might still be present, not just as isolated stars but as the dominant form of mass in galactic halos. Even if boson stars don't make up the entire halo, smaller, more compact boson stars could be wandering through it, influencing the motion of stars and gas clouds as they pass. Unlike black holes, they wouldn't accrete material in the same violent way, and they wouldn't radiate X-rays. They would be stealth objects, detectable only through gravitational effects, tugging on stellar orbits, bending light subtly, and adding mass where no light should be. For example, observations of globular clusters and stellar streams sometimes show irregularities in motion, stars speeding up or slowing down as if nudged by invisible hands. Could these nudges come from compact boson stars drifting through the galactic halo? Some simulations suggest it's plausible. A boson star of a few solar masses could pass through a stellar stream and leave behind a gravitational scar, a deviation in velocity or position. If we mapped enough of these scars, we might reconstruct the population of dark objects that caused them, potentially distinguishing between black holes, dark matter clumps, or something more exotic, like boson stars. Another possibility is that boson stars might sit quietly at the centers of dwarf galaxies. Dwarf galaxies, with their low luminosities and high dark matter content, are fertile ground for spotting dark structures. Many of them exhibit central density profiles that contradict standard cold dark matter predictions. A central boson star could explain these flattened cores, providing the gravitational punch needed to hold the galaxy together, but in a smoother, more distributed way than a black hole would. And there's a speculative twist. If boson stars formed in the early universe, and if some of them survived to this day, they could have accumulated into dark star clusters, groups of invisible stars orbiting each other in slow, gravitational dances. These clusters would emit no light, no heat, and very little radiation, but they'd curve space-time, and their presence would show up in gravitational lensing and stellar kinematics. Lensing, in particular, is a powerful tool for tracking invisible mass. When light from a distant object passes near a massive body, it's bent, creating arcs, rings, or distortions. Compact boson stars, though difficult to spot directly, could betray themselves by lensing background stars or galaxies. Observatories like the Vera Rubin Observatory, LSSD, with its deep, repeated sky scans, might eventually detect such anomalies, tiny distortions inconsistent with black holes or normal dark matter, pointing instead to something field-like and diffuse. And let's not forget the Milky Way itself. If a boson star lurks in our galaxy's halo, it could subtly tug on the orbits of stars in the outer disk, influence the dynamics of satellite galaxies, or perturb the paths of passing molecular clouds. Over time, these small effects add up. With instruments like Gaia, which maps stellar motions with unprecedented precision, we are beginning to see deviations that may hint at unseen structures. There's also the tantalizing idea that rogue boson stars could occasionally pass through the solar neighborhood, rare events, but not impossible given the billions of years of galactic evolution. Such an encounter wouldn't be catastrophic. Boson stars don't interact electromagnetically, so they wouldn't cause radiation storms or tidal disruption. But their gravity might shift the orbits of comets, subtly perturb the Oort cloud, or slightly warp the trajectories of spacecraft. If tracked in real time, it would be one of the most extraordinary discoveries in human history, a visit from a relic of the quantum cosmos. So, could boson stars still be out there? Not just could they may be everywhere, hiding in halos, embedded in dwarf galaxies, drifting between stars, shaping galactic structure in subtle, persistent ways. They wouldn't shine, they wouldn't burn, and they wouldn't collide with gas the way baryonic objects do. But they'd pull, with the same invisible hand as black holes, but without the event horizon or the finality. Their fingerprints would be faint, buried in stellar motions, gravitational waves, and lensing distortions. But with the rise of precision astronomy, machine learning pattern recognition, and deep surveys of the sky, we may be on the verge of finally spotting them, not with our eyes, but with our equations. And when we do, we might realize that the unseen mass of the universe was never just a sea of particles. It was structured, coherent, and shaped by quantum fields from the very beginning. Boson stars still out there. Still hiding. Still shaping the galaxies we thought we understood. Let's imagine a chilling alternate reality. One moment, the sun is shining, its familiar glow warming Earth, illuminating the skies, driving weather patterns, and powering photosynthesis. Then, without warning, without sound or spectacle, it disappears. Not obliterated. Not turned off. Simply replaced. In its place, a boson star. This is no ordinary object. It gives off no light. It radiates no heat. It has no fusion at its core, no corona, no solar flares. It's a sphere of pure gravitational presence, made not of atoms, but of bosonic quantum fields tightly bound by gravity. Smooth. Silent. Invisible. Would we realize it instantly? Would the world panic in darkness? Or could this ghost star hide in plain sight, tricking us into thinking the sun is still there, at least for a moment? To answer this, we must unravel what would happen in such a surreal cosmic switch. First, the gravity. Boson stars can have mass. That's the key to this entire thought experiment. If our replacement boson star had the exact same mass as the Sun, the gravitational pull on Earth and the other planets wouldn't change. Orbits would remain stable. Earth would continue its elliptical path around this new object, unaware, at least gravitationally, that anything had changed. There would be no tidal disruptions. No sudden ejection from the solar system. The Moon would keep orbiting Earth. Jupiter would maintain its dance around the new center. Gravity, our most faithful cosmic constant, would remain unchanged. Newton wouldn't notice. Einstein wouldn't blink. So from a purely orbital perspective, everything would seem normal. That is, until... Then comes the darkness. The moment the sun is replaced by a boson star, the light stops. Not gradually. Not like sunset. Instantly. Because boson stars don't emit photons. They don't burn. They don't glow. They have no photosphere, no plasma, no nuclear furnace. The only force they emit is gravity, and possibly gravitational waves if they oscillate or rotate, but not light. We wouldn't notice the darkness immediately, though. It takes about 8 minutes and 20 seconds for light from the sun to reach Earth. So for just over 8 minutes after the switch, Earth would still bask in solar rays emitted by a star that no longer exists. Then darkness. Day would turn to night across the entire planet simultaneously. The skies would blacken. Birds would fall silent. Animals would grow confused. Temperatures would begin to plummet. It would be unlike any eclipse. Total, sudden, global, and permanent. Cities reliant on solar power would lose energy input instantly. Crops would no longer photosynthesize. The sky, previously blue from scattered sunlight, would become pitch black, except for stars, which would begin to pop into view in broad daylight. That alone would trigger global panic. The thermodynamic collapse. Let's say humanity somehow remains calm, perhaps believing it's a strange celestial event. But the real catastrophe comes next. The sun radiates about 3.8 x 10 superscript 2 watts of energy. Every square meter on Earth receives about 1,360 watts when directly exposed. This energy keeps Earth's surface temperature stable, maintains our climate, drives winds, warms the oceans, and supports nearly every ecological system. Without it, Earth begins to cool rapidly. Within a week, global average temperatures would drop below freezing. Within a month, oceans would begin to freeze at the surface. Within a year, Earth's atmosphere would start to condense and collapse, especially the upper layers. Only geothermal energy and human-made infrastructure could provide localized warmth, and that wouldn't be enough to support civilization as we know it. In this eerie world orbiting a dark ghost star, humanity would be forced underground or to heated shelters, desperately trying to survive a long, endless winter. And yet, even then, the planet keeps orbiting. Silently. Elegantly. Around something it cannot see. Could we even detect it? Let's say the sun was replaced by a non-interacting boson star of identical mass. Its gravitational footprint would be indistinguishable from the real sun. It wouldn't accrete matter violently like a black hole might. It wouldn't distort spacetime in visible ways. If it's not spinning rapidly or merging with another object, it might not emit detectable gravitational waves either. From Earth, there would be no direct way to see it. Telescopes wouldn't catch any glow. There'd be no solar spectrum to study, no sunspots to monitor. The sun's spectral lines, the fingerprints of its elemental composition, would vanish. We would be left with a perfect gravitational stand-in, invisible and intangible. Could we infer its presence? Yes, but only by its gravitational effects. If it moved slightly or caused gravitational lensing of distant starlight, we might deduce its mass. If spacecraft near the sun's former location continued to feel gravitational pull, we'd suspect something was still there. But without light, confirmation would be frustratingly difficult. And then there's another eerie consideration. A boson star might trick our telescopes. Some models suggest that boson stars can mimic the gravitational lensing of black holes, forming shadow-like effects under certain conditions. If it's dense enough, almost as compact as a black hole but without an event horizon, it might bend light around it to form a photon sphere, casting a shadow visible with powerful radio telescopes like the Event Horizon Telescope. Imagine turning such a telescope toward the now dark spot in our sky, expecting to see the solar disk, and instead finding a warped ring of bent starlight, like the one captured in the M87 image. A ghostly lens. A perfect gravitational doppelganger. Even more bizarre, a rotating boson star could form a torus of field density, making its shadow asymmetric or ring-shaped. It might not look like a sun at all, but like a rippling quantum void. The psychological impact. In this alternate world, Earth would be caught in a paradox. The gravitational force says the sun is still there. The absence of light says it isn't. How would humanity process this? Religions would erupt with theories. Conspiracy movements would explode. Scientists would scramble to create new instruments. Space agencies would redirect every telescope and probe to the source. This would be unlike any crisis Earth has ever known. Because it wouldn't just be environmental, it would be existential. We would come face to face with something we didn't understand. Something that contradicts what we thought a star should be. A stellar object that doesn't shine. A mass that curves space, but emits nothing. A reminder that the universe isn't built to suit our senses. The quantum horror. The final chilling realization might come when physicists identify what the object is. They model its gravitational field. They test various dark matter distributions. They simulate its compactness. And they reach a conclusion: it behaves like a boson star. A quantum field object made of particles we've never observed directly. Something that exists not as matter, but as a standing wave of mass energy. And then, the obvious question: where did it come from? Boson stars don't form like regular stars. They don't ignite from dust clouds. They don't live and die like main sequence objects. They emerge from extreme conditions, perhaps the early universe, perhaps from the collapse of exotic fields. So how did one just replace the sun? That question might never be answered. And the silence of the boson star would make it worse. It would give us nothing. No signals. No flares. No screams. Just presence. Presence without substance. Mass without matter. A body made not of particles, but of probability. And it would remain there. Forever. Orbiting quietly. Curving space. Mocking light. A star that burns with no fire. That binds planets with no fusion. That reminds us, every cold day, that not all stars shine. If humanity were ever to confirm the existence of boson stars, not as theory, not as speculation, but as observed and catalogued entities, it would mark a turning point as profound as the discovery of black holes or the cosmic microwave background. It would not simply add a new object to our celestial inventory. It would redefine what we think matter can be, what the structure of the universe actually includes, and what it means for something to exist. For centuries, we've understood stars as radiant spheres of thermonuclear fire, objects governed by fusion, pressure, and light. They fit within a framework of physics where matter is built from fermions, protons, neutrons, and electrons. Even our most exotic objects, white dwarfs, neutron stars, and black holes, emerge from the gravitational collapse of that same fermionic matter. But boson stars offer an alternative vision: matter as wave. An entire macroscopic object, not made of atoms, but of a coherent quantum field. No discrete particles bouncing around. No surface. No core. Just a cloud of probabilities shaped by gravity. To confirm boson stars would mean embracing this eerie, almost metaphysical reality. That mass can exist without structure, that stability can arise from quantum harmony instead of atomic balance. They would stand as real-world examples of quantum field theory on astrophysical scales. Instead of being confined to particle accelerators and theoretical papers, these fields would take center stage in the cosmic drama. This wouldn't just affect astrophysics. It would ripple outward into fundamental physics, potentially uniting gravity and quantum mechanics in new and profound ways. Boson stars are solutions to equations that merge Einstein's theory of general relativity with complex scalar fields, a step toward the elusive theory of quantum gravity. Observing them would validate this union. It would give physicists empirical evidence that space, time, and matter can coexist in wave-like harmony. And then there's the question of identity. What are these bosons? If boson stars exist, the particles making them up must also exist, but they're not part of the standard model of physics. They'd be new bosons, perhaps axions, perhaps dilatons, perhaps entirely undiscovered fields predicted by string theory, supersymmetry, or other beyond standard model ideas. In this light, boson stars wouldn't just be strange astrophysical objects. They'd be laboratories of new physics, proof that the universe contains fields and particles we've never touched, never seen, but which shape galaxies and bend light. They would be like fossils of the early universe, ancient structures formed from fundamental forces that shaped everything. Dark matter, too, would come under renewed scrutiny. For decades, scientists have suspected that dark matter might be composed of weakly interacting massive particles, WIMPs, sterile neutrinos, or primordial black holes. But these searches have come up empty. Boson stars offer a fresh perspective. Maybe dark matter isn't granular at all. Maybe it's field-based, coherent, and wave-like. Maybe the dark mass holding galaxies together is not made of particles at all, but of enormous, invisible stars made of force and silence. In this scenario, the universe is not built from billiard balls. It's built from quantum ripples, from oscillations in fields that never interact with light but still hold mass, momentum, and gravitational power. It would be a ghostly revolution in cosmology. We'd have to rethink the early universe. If boson stars formed shortly after the Big Bang, their presence would change the story of structure formation. Galaxies might have formed not from gas coalescing under gravity alone, but around pre-existing gravitational wells formed by these stars. The cosmic web itself might trace the faint latticework of bosonic structures, dark, massive, and eternal. Even black holes, once thought to be the ultimate gravitational mystery, would have to share the throne. Boson stars mimic black holes in many ways. They can bend light, hide in shadows, and create event horizon-like illusions. Some of the black holes we think we've found might actually be these ghost stars in disguise. Confirming boson stars would force astronomers to revisit decades of data. Every candidate black hole would need a second look. And perhaps most radically, boson stars might blur the boundary between matter and energy. Unlike stars, which emit light and die, boson stars can remain stable indefinitely. They don't evaporate like black holes. They don't collapse like white dwarfs. They exist in a kind of gravitational balance, perpetually on the edge of wave and particle, presence and absence. In this way, they are cosmic whispers, made not of atoms, but of possibility. If we proved they were real, the implications would reach deep into philosophy as well as physics. What is real, if something can exist without light? What is matter, if it can behave like a probability cloud? What is time, if an object can last forever, unchanging, untouched? The ghost star revolution wouldn't come with a bang. It would come with a whisper, a quiet recognition that the universe is not what we thought. That the stars we see are only a fraction of what's out there. That some stars are made not of light and heat, but of coherence and gravity. And that in the dark spaces between galaxies, the true architecture of reality may be hidden in the silence. Boson stars are not made of flame. They do not roar like the sun. They do not churn with plasma, erupt with flares, or blind with brilliance. Instead, they hum with gravity, whisper with quantum grace, lurk in the shadows between stars, composed not of matter, but of mind-bending mathematics brought to life by the universe itself. They are stars made of silence. Their presence is not measured by photons or heat, but by the warping of space-time. A nearby star that curves just slightly too much. A lensing arc that bends without a cause. A planet that orbits nothing seen. a gravitational wave that ripples without a crash. And from these clues, these delicate fingerprints, we are beginning to listen. To imagine a boson star is to accept that something can exist not through substance, but through structure, that a mass can emerge from pure field interactions. That an entire celestial body, massive and stable, can exist without a single atom, without light, without the touch of fire. That form can arise from symmetry alone, and be held together not by touch, but by quantum rules and invisible threads of force. It is one of the most profound reversals in scientific thought since humanity first looked at the night sky and named the stars. And it may be real. They don't fit in our telescopes easily. They don't leave thermal signatures. They don't call attention to themselves. But their effects might be everywhere, shaping galaxies, whispering through the void, reminding us that existence is far broader than perception. Boson stars may be the cosmic sculptures of fields that dance in synchrony, that move in step like a Bose-Einstein condensate spanning kilometers or even light years. Structures born from particles that don't push each other away like fermions, but embrace, overlap, merge into unity. They are, in many ways, the physical embodiment of harmony, objects whose entire being arises from a perfect balance between attraction and coherence. Between gravity pulling in and quantum pressure pushing out. No collisions. No chaos. Just a star-shaped equilibrium of possibility. And perhaps most beautifully, boson stars are a promise. A promise that there are still things in the universe we haven't seen, not because they are far away, but because we've never thought to look for them in the right way. They are a reminder that our maps of the cosmos are still being drawn. That behind every gravitational mystery, every cosmic silence, there may lie a new kind of object, unseen, unlit, but no less real. They may live in the halos of galaxies. They may pass between stars. They may mimic the shadows of black holes. They may have been here since the beginning. They may outlast the last dying red dwarfs. They may be the first and last stars the universe will ever know. They are not made of atoms. They have no surface. They have no light. But they are made of the fabric of reality itself. Not stars of heat and fire, but of symmetry and silence. And in that silence, they might hold the loudest secrets of the cosmos. Secrets about the quantum foundations of the universe. Secrets about dark matter and missing mass. Secrets about how gravity and quantum theory can be married not just in equations, but in the sky. Secrets about how something can be made from almost nothing, and still be everything. So the next time you look up at the stars and count their lights, remember, there may be more stars in the sky than light will ever tell you. Some of them are ghosts. Some of them are echoes. Some of them are boson stars. Stars made of silence. Of whispers in quantum fields. Of force without flame. And in that silence, they just might contain the next great revelation of science. The greatest truths, after all, are not always shouted. Sometimes, they are whispered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.